First is that several people have asked about presentations. They will be distributed and posted online after the conference is over. That just wanted to note that, as well as the presentations are being recorded, and we will probably post those at a later date as we'll need to separate them. If anyone does have concerns with their presentation being posted, please talk to one of the organizing committee members, which is Liam, Gumley, Graeme Martin, and Just Braun. The other note is I will be resolving some of the questions from Slido that have been answered, but once again, if you would like to use Slido to answer questions, you can go ahead. So we'll start with our first presentation. This morning session, we'll talk about various CSPP packages from CSPP-LEO and CSPP-GEO. So our first presenter is Liam Gumley from SSEC CIMSS, and he'll be talking about CSPP-LEO.
Thank you, Jess, and welcome back for day 2. So my job this morning is to talk about recent progress with the CSPP-LEO software suite, what we can do today, what we're working on, and some recent innovations that we've made within the direct broadcast LEO area at SSEC. So I first want to recognize our excellent team of developers, testers, user support people. Their names are all on this slide. Many of them are in the room right now. We couldn't achieve all the progress that we've made in CSPP-LEO without this excellent team supporting us. So I want to recognize in the room, Jeff, Matthew, Jess, and Graeme. So, not really CSPP-LEO related, but I just wanted to cover some of the changes that have happened in our field since the last time that this group met in June 2022 in Madison. So there's a lot has happened. CMA has launched 3 new FY3 satellites. In June of 2023, the NASA Direct Readout Lab closed down most of their operations, but they are still supporting some of the ancillary data sets that are used by IPOP, and Lihang has a poster out in the hallway that talks about that. In November of 2023, NOAA 21 was declared operational. In May 2024, Terra, which is still operating today, had the direct broadcast system shut down because of power issues on board the spacecraft. In August of 2024, the Arctic Weather Satellite was launched and is operating very successfully, the precursor to EPS Sterna. And then in the middle of 2025, we said goodbye to 2 of our old friends, NOAA 18 and NOAA 19. Some tears were shed, but we wish them well on wherever their journey takes them, and we're pressing ahead without them. Then in August of last year, MEDOP SG-A1 was launched to great success. And I already mentioned the FY3 satellites that have been launched by CMA. So a lot has happened in the last 3 years, even 4 years. So CSPP, and I'm focusing on LEO, Graeme will give us the update on GEO. So CSPP-LEO is a suite, a collection of freely available software for processing data received usually by direct broadcast from polar orbiting Earth observation satellites, weather satellites in particular. Primarily the JPSS satellites, but we support other satellites as well. And we support the calibration of calibrated observations, sometimes known as level 1B. We also support the creation of geophysical derived products, land, ocean, atmosphere, and also a wide variety of imagery from imaging sensors and sounders. And I should note that CSPP-LEO is funded by NOAA JPSS and the LEO program, and Lihang and Satya are in the back of the room. We couldn't do this without the support of our funding sponsors at NOAA. So the website is on right there. Use your best search engine to find it, and you can access all of the software that I'm going to talk about. So CSPP supports users all around the world. Typically, they are associated with an antenna like one of these. And many of you in the room operate antennas like these ones. These happen to be stations where CSPP is processing the data. On the left, it's the CONAI antenna in Cordoba, Argentina. In the middle, it's an antenna at a university in Dhahran in Saudi Arabia. And on the right-hand side, that's an antenna at Union Glacier, actually run by a tourist operator in Antarctica. But nevertheless, in all those different environments, CSPP is there supporting processing and generation of products. So we keep track of everyone who registers to download CSPP Leo. This is an update on the data that we've collected to date. As of last week, there were about 3,700 registered users, and we've tracked downloads to more than 100 countries. So we believe it's used on all continents, including Antarctica, and it's used by many operational agencies, including EUMETSAT, of course, Media France, BOM, Met Office, Environment Canada, KMA, JMA, IMD, and we have representatives of some of those organizations in the room. So the features of CSPP Leo have mostly remained constant since we began the project back in 2011. So most importantly, perhaps, we use NOAA NESDA STAR enterprise algorithms and software to support JPSS and other satellites. The job of the CSPP is not to develop that software. We adapt it as needed to run in a direct broadcast environment, integrate it, test it, document it, release it, and provide user support to the community. We support multiple satellites and sensors where it's feasible. Obviously, our primary job is to support JPSS, SUMI NPP, NOAA 20 and NOAA 21, but where NESDIS has developed support, let's say in a sea surface temperature retrieval product for AVHRR, or even MODIS in some cases, we will enable that support in the CSPP package. We've always provided software that's ready to run, so it's compiled. Our current supported platform is Rocky Linux 8. We will likely be updating our base platform, our base operating system soon, because Rocky Linux 8 is no longer receiving, it's still receiving security updates, but it's coming up on its end of life. So we'll need to update that platform. The CSPP packages, without exception, are easy to install and easy to run. So once you've downloaded the tar files and you've unpacked them, within about 10 minutes, you should be able to set a couple of environment variables and run the software. It doesn't take all day to install it and run it. And we've always featured very prompt, friendly, and expert user support when there's a problem that we hear about from our users in the field. So as of today, the satellites that are supported in some way within CSPP Leo include the 3 JPSS satellites. And on board those, NOAA 21, NOAA 20 and SNPP, we support VIIRS, CrIS, ATMS, and OMPS, the ozone sounder. For MEDOP B and C, we support all the ATOV sensors, the sounders, and we also support AVHRR, although I'm not sure that the VIIRS is actually doing anything useful at the moment, but nevertheless, we have software that supports it. For EOS, in terms of direct broadcast satellites, we support MODIS and AIRS. We do still support Terra in some ways, but Terra is not really a direct broadcast satellite anymore. We have support for the GCOM W1 satellite, and in particular the AMSA2 microwave imager. And for FY3D, we support creation of imagery from Mercy 2 and also Mercy LL. And I'll show you examples of lots of these products from these satellites. So in terms of the products that we support, the first product, and for JPSS, maybe the most important, is the sensor data records, which is the equivalent of level 1B. So that's the calibrated and geolocated observations from VIIRS, CrIS, ATMS, and OMPS. And in one package, one software package called CSPP SDR, we provide support for 3 satellites and 4 sensors. So it's actually a suite of 12 different sensors. Our plan going forward is to maintain that for JPSS 4 next year, which will become NOAA 22, and then NOAA 23 or JPSS 3 in about the 2030 timeframe. And Matthew, put your hand up. Matthew, where is he? There he is. Matthew is the primary engineer who's responsible for CSPP SDR. He has a very nice poster in the hallway about some very nice tooling he's developed to make the build process repeatable and version controlled. So check it out and talk to Matthew about the details. We also support creation of imagery from many of the products, either at level 1B or at level 2. Imagers, sounders, using a software package called Polar to Grid, which I'll talk about a little bit. And we'll have a recorded presentation from my colleague, Kathy Strabala, on Polar to Grid coming up in this session. We support the creation of many of the NOAA NESDIS atmosphere products, clouds, aerosols, volcanic ash, temperature and moisture profiles, trace gases, precipitation, snowfall rate. And then for land situations, we support the creation of the retrieval of active fires, surface reflectance, vegetation indices, flood detection, snow CrIS via properties, primarily from VIIRS, but in a couple of cases from other sensors as well. And then for ocean, we support the retrieval of sea surface temperature and sea ice parameters. Once again, all of these are using NOAA NESDIS derived, NOAA NESDIS created algorithms and software that we've wrapped and released for CSPP LEO. So this is the master list of CSPP LEO software packages as of today. We have some others that are now considered deprecated that we don't provide active support for, but these ones we provide active support for. So at the top of the list is sensor data records, SDR, current version is 4.1.1. The second one on the list has been new in the last year or so. It's the VIIRS Radiance Clusters, which is mostly of interest to people who are doing NWP data assimilation. It basically provides VIIRS radiance statistics within each field of view of the CrIS sensor. And that's something that has been requested by the NWP community for a long time. NOAA has developed a very good solution for that. We've now adapted that to run within CSPP. I won't go through all the other entries on the list. I might point your attention to the last entry on the list, which is RT-STPS, formerly developed and maintained by NASA, but with the demise of the Direct Readout Lab, CSPP LEO now provides support for RT-STPS. And our primary job with RT-STPS is to support the JPSS satellites. However, as we're able to provide support in the form of configuration files for other satellites, such as MEDOP SG-A1, for example, we're happy to provide that, but our primary job is to support JPSS. So just speaking about processing of JPSS satellite data, and this is most relevant to someone who's receiving all 3 JPSS satellites on their DB system. The recommended service specs today, if you want to process all of those data sets, VIIRS, CrIS, ATMS, and OMPS, you need a significant server, a strong server. We'd recommend at least 96 cores, Intel or AMD, 256 gigabytes of RAM, and fast solid-state drive for hosting your Scratch space, your workspace, and Rocky Linux 8. You can use maybe Rocky Linux 9 or one of the compatible Red Hat distributions, that's fine. And of course, if you're using a container like Aptainer or Docker, there's more options as well. But Rocky Linux 8 is the base platform that we guarantee it will work on. So make sure you have a strong server. And we appreciated the comments from Tobias yesterday about his benchmarking of how many cores do you need to use to run the various CSPP packages efficiently. So thank you for doing that work. So I will mention the CSPP LEO releases that we've had in the last year, back to the beginning of 2025. And this is one of 2 slides. So in March of this year, we released an update for the SDR package that was relevant for ATMS. And it was a geolocation correction that was developed by NOAA, deployed by NOAA in their operational processing. And we provided that same update as a patch to the SDR software. So if you are processing ATMS data from any of the 3 satellites, I strongly recommend that you install SDR v4.1.1. Also in March, we released Polar to Grid 3.2, which expanded the range of products that are supported for creating imagery, including some of the new VIIRS environmental data records, level 2 products that were adapted from NOAA to be in CSPP. And it also adds readers for AWS data and for the AMSA2 GASP Level 2 products. In January, we released the VIIRS CrIS suite that derives several parameters related to snow cover in cold environments, and it added support for NOAA 21. In fact, over the last 2 years, our primary focus has been adding support for NOAA 21 in especially the Level 2, the EDR product suites. In December of last year, we released an update to the Surface Reflectance and Vegetation Index software package for VIIRS that added support for NOAA 21. In December of last year, we released an update to the HEAP temperature and moisture profile retrieval package, adding support once again for NOAA 21. And HEAP actually came up in the presentations yesterday several times, in particular the trace gas retrievals that are possible using the HEAP software package. And in fact, later today, I believe Professor Mitch Goldberg will give us a presentation on some of the recent innovations that he's developed regarding retrieval science using machine learning. And we look forward to that presentation. I already mentioned the VIIRS Radiance clusters. It was released in August of last year. In July of last year, we released the VIIRS flood detection supporting NOAA 21. And we'll have a presentation on that, I think, tomorrow. In June, we released an update for ACSPO, the Advanced Clear Sky Processor for Oceans, that added support for NOAA 21 to that SST retrieval package. Back in March of last year, we released an update for the Atmosphere product suite, so that includes clouds, aerosols, volcanic ash, to add support for NOAA 21. And I think that's the end of the list. So now we'll get to some of the fun stuff, which is images showing examples of the products that have been released through CSPP in the last year or so. So this one is from NOAA 21. This is a true color image from polar to grid, but I must emphasize that this was received via direct broadcast on our antenna in Puerto Rico, processed on site by CSPP SDR and polar to grid, automated. So there wasn't any human doing custom processing. This is part of the automated product suite from CSPP from a DB antenna. This is an example of the NOAA 21 active fires from CSPP. And I think we heard at least one presenter yesterday talk about active fires from VIIRS. This one was actually received on our antenna in Miami, Florida, processed on site by CSPP SDR, active fires v2.1, and imaged by polar to grid 3.0. So polar to grid, as well as creating the background imagery, this nice atmospherically corrected true color imagery, it has a facility for overlaying the fire locations on top of the image, which is a really nice capability. This is an example of the VIIRS flood detection product in the Mississippi Delta and Ohio and Mississippi River tributaries. This was back in February 2025, where there was some significant spring flooding. Once again, this was data that was received by direct broadcast at SSEC, processed on site by CSPP SDR and the VIIRS flood detection software within probably 30 minutes of the reception of the data. So in this particular image, which is color coded according to the different water conditions, anything that is red or yellow is what's considered not normal water cover. So in other words, covered by flood water. If it's blue, that's normal river water, but anything that's yellow or orange or red is considered to be flood water. These are examples of the VIIRS cloud products, the NOAA Enterprise Cloud products from NOAA 21. On the left-hand side, we're looking at cloud top temperature, and the blue and green colors are the high clouds, the orange, brown colors are the low clouds, and on the right-hand side is from the same pass, a daytime pass back in June 2024, showing the aerosol optical depth retrieval. And on the lower left, I can't really point to it, on the lower left of the aerosol optical depth image, there's actually some pretty significant smoke that's influencing the AOD, probably coming from fires in Central America and Mexico. So this image is showing the VIIRS sea surface temperature retrieved by the CSPP ACSPO package. That's the NOAA Enterprise sea surface temperature retrieval that supports all 3 GWSAS satellites. And not in the current version, but in the previous version of ACSPO, there's support for MODIS and also for MEDOP AVHRR. But this happens to be the NOAA 21 sea surface temperature from at least 2 and maybe even 3 passes received. I think these would have been received by our antenna in Puerto Rico, processed on site by VIIRS ACSPO, and then imaged by polar to grid. So you can see at the bottom left some really interesting features related to the Gulf Stream here in springtime. So this is an example of the NDVI product from the CSPP VIIRS surface reflectance package. So this one would have been received at SSEC. This is in August of last year, so summertime. Everything's very green up in the upper Midwest, and as you get off to the west, the US west, it's a little more dry, and those are the brown colors in the NDVI color scale. The green color scale, the green colors mean, heavy vegetation cover. And where it's white, that's areas that either weren't seen by the satellite or that are covered by cloud. So once again, this was processed on site at SSEC with SDR, the VIIRS land surface reflectance, and then imaged by polar to grid. And note that polar to grid now is used actually in the user documentation for this package and other CSPP level 2 packages to show you exactly how to create an annotated high-quality image with a custom color table like the one you're seeing here. And by the way, we give a shout-out to the SatPy team. There's probably some SatPy developers in this room for all the work that they do to support the many different satellites and products, and Polar to Grid uses SatPy under the hood to provide support for those satellites and products. So this is an example of the Mercy 3 low-light imagery from FY3E, imaged within polar to grid. This is data that we received at SSEC and on-site using the level 1 software from CMA and then imaged by polar to grid. You may know that FY3E is in an early morning orbit, so it has a low-light imager so that you can see features in the imagery even when the sun is at very low elevation. This is an example of the microwave retrievals from NOAA 21, from NOAA 21 ATMS in particular, using the NOAA VIIRS retrieval package adapted for CSPP. So this is data that was received by our antenna in Honolulu, Hawaii, processed on site with SDR and VIIRS 4.0. On the left side, we can see the temperature field at 840 hectopascals. And you can see that's fairly warm in the lower part of the image. The temperature is around 295 Kelvin. And on the right-hand side is the corresponding water vapor mixing ratio retrieval at 840 hectopascals. And you can see that it's quite moist to the south of the Hawaiian Islands, but much drier to the north. And then this is another example, also centered over Hawaii. It's maybe a little difficult to see, but in the center of the image, you can see the chain of Hawaiian Islands. So Oahu is exactly in the center. This is actually from the storm-centered imagery suite that is produced on-site at Honolulu and a number of our other antenna sites. And Douglas Schumacher, who's in the audience, will be giving a presentation on products like this tomorrow. And Jeff, who's also in the room, had a role in creating this imagery. But this is an interesting case from Honolulu because they've been having really extreme rainfall over the last couple of months that's caused significant flooding in Hawaii, and particularly in Oahu, where the bulk of the population is. So this is actually a time sequence of rain rate derived from CSPP VIIRS, from microwave sounder, and then from GASP, which is derived from the AMSA2 microwave imager. So this is all from the same day, from the 16th of May, just like 5 days ago. So it's a time sequence starting at 2013 on the top left with the MEDOP-C rain rate retrieval from CSPP VIIRS. Then to the right of that is the ATMS retrieval about 3 hours later. And then you have in very quick succession on the lower left, the rain rate retrieval from AMSA2 at 2335, from the GASP software, and you'll note the difference in resolution between the ATMS retrieval at top right and the AMSA2 retrieval at bottom left. Seeing you're looking at the same storms, the same features, but obviously the microwave imager has a much higher resolution. And on the bottom right, 2341, the retrieval from NOAA 20 ATMS. So why is this significant? Well, it's significant for the National Weather Service in Honolulu because my understanding is that their radar system has a range of less than 200 miles, and it's centered in Honolulu. So each of these grid squares, correct me if I'm wrong, Douglas, is about 2 degrees. And the grid square of 2 degrees is about 200 miles. So more or less, the radar can't see more than one of these grid boxes out to sea from the center of that image. So all of that rainfall that is to the southeast of Honolulu, I can't tell you which direction it's heading from this image, but that rainfall, they can't see it from radar, but they can see it from satellite. And by using direct broadcast data, they can see it within about 15 minutes after the satellite has observed it. And they might get a sense of this rainfall from GEO, but GEO doesn't have microwave. At least we don't have it at this time. So this is the way that the forecasters can see it in real time and use it in their forecasting data suite. And then this is just the same case. These are now both from AMSA2, same date, same time. On the left side is the rainfall retrieval that we saw previously, but on the right side is the surface wind speed that's retrieved from AMSA2. And that provides additional information for the Weather Service as well, because they don't have an easy way, unless they have radar available, of knowing what the wind speed might be. So that's another useful feature, both in Honolulu and also in Guam. Thank you, Jess. So in terms of upcoming CSPP releases CSPP LEO releases that we're working on, we are working on, I won't go through the whole list, but we are working on an update for RTS-TPS. There are a few small code changes, but we're going to include some configurations for MEDOP SG1 and the Arctic Weather Satellite. We're getting ready to release an OMPS ozone and aerosol product using the NOAA OMPS retrievals. And we've already provided a release candidate version of that to our colleagues from GINA and from FMI, who are big supporters and big users of that product. So we look forward to releasing that soon. Later this fall, we'll be releasing the OMPS Level 2 sulfur dioxide retrieval, which is important for volcanic ash monitoring. We'll be releasing the GASP suite with support for AMSA 3, which is now operational, and a number of other releases over the next 12 months. And in summer of next year, we're hoping to release the first version of the next generation fire system supporting VIIRS, which was developed by NOAA. So this is just a quick example of the OMPS total ozone retrieval. On the left side, this is the NOAA operational retrieval displayed in NOAA's JSTAR mapper. And on the right is the corresponding CSPP product using the same software from NOAA, but adapted to work in DB. So on the right side, it's the DB data received at SSEC. And you can see they correspond extremely well. This is a recent event from early April when there was a significant ozone intrusion to the north of the USA in Canada. This is just a preview. This is not from DB data. This is an example of the NOAA OMPS sulfur dioxide product over the Hawaiian Islands. And this is actually from just a few days ago when Kilauea was erupting. And you can see the SO2 retrievals. The units here are Dobson units, up to 10 Dobson units of SO2 floating around. This is total columns, so it's a little hard to say what level it's at, but it can be a health concern, particularly in Hawaii and other places in the world as well, obviously, where they have active volcanoes. This is an example of the snowfall rate product that we're working on to release for CSPP. This is the microwave radiometer derived product from actually the Arctic Weather Satellite, but this is the snowfall product actually over the upper Midwest, including Wisconsin, from a significant snowfall event that we had back in March of this year. So this product will be coming from CSPP as well. Okay, so just a few more slides. I wanted to point out in general some of the innovations that we've been working on recently related to direct broadcast at SSEC. The first one is the antenna control system that we've developed by Bruce and deployed and tested by Douglas. There's a very good poster that has the details out in the hallway. Some of you may have seen that we have some MEDOP SGA1 imagery and Arctic weather satellite imagery displayed on those posters. We are now receiving routinely every day MEDOP SGA1 and AWS, receiving it, decoding it, and processing it on site. We've been now for several years as part of the DBNet project disseminating full spectral channel sets from IASI and CrIS via WIS 2.0. So we've been working very closely with WMO and also EUMETSAT on coming up to speed on WIS 2.0. We've also been enhancing our ultra-low latency fire detection, and Bruce will be giving a presentation on that tomorrow. Bottom line is we can observe, calibrate, geolocate, and detect wildfires with VIIRS over North America within 45 seconds of observation on the spacecraft. So I don't mean at the end of the pass, I mean after the satellite observed the fire. If there's a fire there, we can detect it within 45 seconds. Excellent, thanks, Jess. We've also just added the capability to create CrIS ultra-low latency data. So that means CrIS calibrated radiances and eventually dual regression retrievals of CAPE, which is a measure of atmospheric instability, within about 60 seconds of observation on the spacecraft. So once again, not at the end of the pass, but after the observation is made by the spacecraft, a CAPE retrieval within 60 seconds. And then lastly, we're working on upgrading all of our antenna sites, the 6 different sites that we support, that we operate, to support MEDOP SGA1 and AWS by the end of this year. So let me just end with the evidence showing you that we are receiving MEDOP SGA1 routinely. This is from the 16th of this month, the daytime pass over the US East Coast. And this is Arctic weather satellite from the 17th of May. This is actually channel 1, I think, showing also the eastern US, just as evidence to show you that we are receiving it and processing it. That's it. Thank you.
All right, thank you, Liam. If someone has one quick question, we will take it. Otherwise, I think we'll defer to the break. And I see no immediate hands, so please feel free to follow up with Liam with any questions you have. And thank you very much for the presentation. Okay, so our next presenter is Graeme Martin. And so we are going to be switching from CSPP LEO to CSPP GEO. So Graeme is a project manager for the CSPP GEO project at the University of Wisconsin, and he forgot his water. I will keep talking while Graeme goes. So we will turn it over to Graeme. Thank you.
All right. Good morning, everyone. So I'm Graeme. I'm the project manager of CSPP GEO, and Liam is the PI. Our group is located at the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin. You'll see the acronym CIMSS in a lot of places. That's what it means. The picture on this slide shows a view from our roof in Madison. So the team members are shown in the box on the upper right. Several of those people are in the room. There's a lot of overlap with the LEO project. And the community satellite processing package for geostationary data, unsurprisingly, creates software allowing users to process data from geostationary satellites. Our primary funding also comes from NOAA STAR, and it comes from the GOES-R program. We do have some additional funding, a small amount of additional funding, which I'll talk about. We provide software to process the raw data, the raw GOES data stream, and also to create imagery and generate higher level products. The table on the right shows the currently available packages. As you would imagine, we support GOES series with most of our software, but some of the packages support other satellites as well. I'm not going to talk about all of these packages. I'm just going to focus on what we've been working on recently and some upcoming releases. So generally, the software supports data from standardized data in standard formats. So you can process data received from direct broadcast, but you can also process data from, for example, NOAA open data dissemination and other sources. Most of the packages are based on code that was developed by science teams that were funded by NOAA, but a few are developed from scratch. And typically, many of the science algorithms come from the ASSIST group as part of our longstanding collaboration with that group at NOAA. Similar to the Leo software, all the software is free to download and use. You just need to provide an email address in order to register. And we try very hard to make it easy to install and run, and to provide high quality documentation. So who are CSPP Geo users? Well, the National Weather Service uses our software. Jess Braun is going to be talking about that later today. A variety of U.S. government groups use our software, as well as groups within the commercial sector, the defense industry, and international med agencies, and science and academia. We provide a number of channels for users to connect with us, including a support email. We maintain a forum on our website. We contact users directly. Anybody who's registered to download software probably has seen multiple emails from me. In this meeting, of course, there's also something called the GRB user group for anybody who's receiving GRB data. This is something you should be aware of and probably a member of. That's maintained by NOAA and Toby Hutchings specifically. It's a way to disseminate information that's of interest to that particular group, and it's also, because it's a mailing list, you can also discuss issues directly with other people who are receiving GRB. And of course, conferences, and occasionally we'll teach a workshop or a training course. So this is a map kind of similar to the one that Liam showed, but for GEO rather than LEO. It shows the locations around the world where users have registered to download our software and actually downloaded the software. Each point is color-coded by the number of users there who registered. So for GEO, we now have more than 2,000 registrants downloading to 79 countries as of a couple of weeks ago. So it really is an international user base. So I want to provide a little bit of background on the GOES rebroadcast or GRB data stream. Anyone who's within the footprint of GOES East or GOES West can receive the GOES data directly via GRB, which of course involves setting up a satellite and a processing system. Data from all of the GOES instruments is included, and it's provided at full resolution. And historically, GRB offers very high reliability and low latency. So how low is the latency? This is just a quick check I did a few years ago on data received. I think it was about 20 minutes of data received on our antenna at the University of Wisconsin. You can see in the yellow box that for all of the instruments other than SUVI, for some reason SUVI takes a little longer. I don't remember the exact reason for that. But for all of the other instruments, the data latency is less than 10 seconds. And that's from the time of the last observation on the satellite to when the product has been generated and is available for use on the user system. So very low latency. The GRB package allows users to process data received, to process the raw GRB data stream. So this is the initial package in the GOES-R processing chain, and it reconstructs those products locally. Then you can run the other software packages to generate higher level products. So I'll just say that the GRB package is basically in maintenance mode. This is a very mature piece of software, one of the very first that we developed. But we do have some recent and ongoing activities related to the GRB package. Sometimes we get, basically anytime there's going to be an update to the GOES-R ground system that might affect GRB, we like to get test data. We run it through the software and check for issues that might potentially affect product generation on user systems. In some cases, we then generate or create a patch and release that to our users. And then we provide feedback to NOAA. So currently, we are participating in preparation for a change that's going to happen at NOAA affecting GRB, which is that they're transitioning both level 1 processing and GRB generation to the cloud. And that's called the Geo Cloud Compute Subsystem, or GCCS. So we have some test data from them that we're testing out now. My understanding is that there should be minimal impacts to users in terms of latency or reliability. That's obviously very, very important for GRB, but we're very interested in monitoring and participating in this. And I don't have an exact timeline, but this is something that's going to happen soon. The AIT framework package produces level 2 products for the GOES-R series ABI. This is based on research versions of the GOES-R product algorithms developed under NOAA funding. We get this software from Assist, the base software. Our latest release was a patch release last year. It included some updates for the aerosol optical depth product that improves it for GOES 19. Also, science updates for the cloud mask and some bug fixes. So this animation at the bottom is just a series of quick looks that can be created with the software package. I'm sorry, this is not a very interesting test case, but it's just what I had on hand. I just wanted to demonstrate the range of products that are available, and those are shown in the list on the top. So this is a very full-featured package that can be used to generate a lot of products. We are working on a new release that will add support for Himawari 8 and Himawari 9, specifically to generate the derived motion winds products, as well as cloud mask, cloud top height, and cloud top phase. So this will be a beta release. Development has been funded by the Central Weather Administration of Taiwan. We've gotten a lot of support from the Assist team. In fact, they did some development on the core software to support this. It will support processing of full disk and target area. Japan region will not be processed. That's simply because it's not supported in the underlying software. In fact, Assist and Mike Butler specifically added support for the target region because that's something that CWA was interested in. And it supports processing of HSD, the HSD data, which is the full resolution cloud distributed data, as opposed to Himawari cast. And just to prove that we can do it, this quick look on the right, it shows derived motion winds from a very early, well, not so early, but it's the current prototype version of the Himawari winds package. Moving on to geo to grid. So Liam talked about polar to grid. This is a geo equivalent maintained by developed and maintained by Dave Hayes, the same person. It allows creation of high quality imagery, including single band, RGB, and now level 2 products. And we try to make it easy and efficient, easy to run and efficient. Alejandro talked about that a little bit yesterday. I know that every new release that comes out, Dave Hayes puts some effort into improving to getting the run speeds down, improving the efficiency of processing. It's based on SatPy, and Dave is an active maintainer of SatPy as well. So it's developed in an open source way. So it's kind of contributing something back to the community. The image on the right this was created by Tim Schmidt, and it shows a dust storm in the western U.S. And we just released, this is brand new, we just released version 1.3 last week. It includes finalized support for GOES 19, ABI, and SCI. It adds product readers for ABI, cloud top pressure, and cloud top phase. And it adds numerous RGBs, as well as optimizations and bug fixes. The CSPP Geosphere website displays tiled ABI imagery in near real time. This is acquired on antennas located on our rooftop, and it's run through a processing system consisting of CSPP Geo software that's running on local cloud equivalent infrastructure that we stood up. It produces a variety of imagery, and the products are generated with very low latency. You can download images and animations, and that's pretty easy to do. So the image on the right shows the FOG IFR product, which is aimed at aviation. And the most recent update to Geosphere was in October of last year. It updates the underlying software and adds FOG products, and also includes some mobile updates. And this is an example of animations that can be downloaded from Geosphere. On the left is AOD. and on the right is true color. You can see at the upper left smoke from the Canadian wildfires. This is in 2025. And you can also see that in the true color image. I think that in AOD, the smoke stands out a little more because of the coloring, and you can see more structure. The ABI flood mapping package is based on science code that was developed by San-Mei Lee. She has a talk later in the conference, and that software comes to us from Assist. By using geodata, you get higher temporal resolution. If you look at the animation on the lower right, shows multiple successive days with a flood map that contains data that was acquired during that day. So what I want to point out is the white is snow, so you can see the snow melting. The yellow and red are flooding, so you can see that changing over time. And then the gray is clouds. And you'll notice there's really not many clouds, which indicates that the instrument is able to obtain a clear view of the surface for most of the area in each of those days. And this is, I think, the same event that Liam showed in his talk. So you can kind of see the value of GEO. It's lower resolution, but better for seeing through the clouds. The current version is 1.0 that was released in January. It supports ABI. It also allows user-definable areas of interest and provides a variety of output formats. And we're planning to start work towards a blended flood mapping package that will be a joint LEO-GEO release. So it'll combine the advantages of GEO and LEO to produce a superior product. That's also based on science code from San-Mei Lee. The Lightning Cast package is based on science code developed by NOAA scientists John Centineo and Mike Pavlonis. Predicts the probability and location of lightning within the next hour. This is based on a deep learning model that's been trained on GLM, but in runtime, you only need ABI data. So on the right is an example image showing lightning contours overlaid on IR cloud phase. It's a very full-featured package. It includes the ability to generate imagery with various RGBs as background using ABI data. So the current version is beta 2. It's still at beta status. It supports GOES and Himawari, generates a variety of outputs. It also supports user-defined areas of interest, which I think is important for direct broadcast users. And we're working towards a version 1.0 production release that will add meteograms, which are point forecasts, updates to the science code, and various other changes. So Levi Fonts, who's sitting next to me here, has a talk. He's the main developer for Lightning Cast, and he has a talk tomorrow. The next generation fire system is an experimental AI-based software system that does early detection of fire and continuous monitoring of fires. It's developed by a science team at CIMSS, led by NOAA scientist Mike Pavlonis and also Jason Otkin. Development is continuously informed by the National Weather Service, forecasters, land managers, and firefighters, and it's been demonstrated within the NOAA fire weather test bed. So we have started work towards a NGFS package. This will be another joint GEO-LEO package, and the science code comes to us containerized. So this is the first release that we're doing on the GEO side that's container-based, but it will behave like a typical CSPP GEO release. You'll be able to run it at the command line as you usually do, so you don't need to know about the containers, but we're hoping it might provide some optimizations for users who are actually running in the cloud. And it's a fairly complex piece of software with a kind of a high cadence of dynamic ancillary data, though not necessarily a particularly high volume. And the image on the right was captured from a GeoTIFF. Well, no, let's see. It was a GeoJSON file that was created from a prototype version, and it's been overlaid on a true color that was created by Geo2Grid. And our initial beta is planned for the fourth quarter of 2026. It will support GOES-R series. and it'll allow user-definable areas of interest, and CSVs and GeoJSON and NetCDF products. And then we're planning on a second beta for first quarter 2027, which will add support for VIIRS. When I say we, I mean the CSPP, Geo, and LEO teams. The turbulence package will predict the probability of moderate or greater turbulence within the next 10 minutes. It's based on code developed by a science team at CIMSS led by Tony Wimmers. So we've started work towards an initial release, and it will support GOES ABI. Potentially, we may support other instruments. That's TBD. And at the right is an example of turbulence map from the CIMSS website that has turbulence contours over the Pacific. So now we're getting into, I guess we've been into the future releases. An all-sky retrieval algorithm is being developed at CIMSS by Zhenglong Li's group. This is under GeoXO funding. The current version supports ABI, but the plan is to add support for IRS, Himawari 10, and eventually GXS, which is the GeoXO sounder. And the plan is for National Weather Service to evaluate the algorithm at hazardous weather testbed in spring of 2027. So these images, I think, illustrate the value of the all-sky retrieval algorithm pretty well. If you look at the image at the lower right, you can see atmospheric moisture from the Gulf going up the east coast of the United States. That is the all-sky retrieval product. Above that is the operational TPW product. This is TPW, the total precipitable water that we're talking about. And in the operational product, you can't see that because it's obscured by clouds. This is in May of 2025, and the end result associated with that is a flash flood that occurred in Maryland a couple of days later. So we're planning to start work on an all-sky retrieval package. The initial capabilities will be TPW for ABI. We may release a beta in 2027 if the algorithm is considered sufficiently mature. And I want to mention that we're trying to work towards the release of experimental capabilities to users, just to get those in the hands of users early on, and to potentially provide a pathway for feedback to go back to the algorithm developers as we shift into the GeoXO era. So that was my last slide. I want to leave you with some links. So if you want to download the software, this is where you can go. And there's a link to the Geosphere website. There's our email address. Feel free to email us. We'd love to hear from our users. You can email me directly. I probably should have put my address in here as well. So that's it. Thanks, everyone.
All right, thank you, Graeme. We do have time for questions. Oh, yes, Alejandro, go ahead.
About the new products, are you planning to add SST and, well, rain rate, you say already, but SST in the L2 products?
We have no plan currently to add SST. It's interesting you should bring it up, because I was talking with Priyanka Roy, who's a member of the ASSIST team, about that yesterday. It sounds to me like that product has matured a lot in the last couple of years for GOES, and it's potentially at the point where we could consider releasing it. It's not going to be released in the next year for sure, but after that, possibly. If that's something you're interested in, we really like to know what users are looking for. So it sounds like you're interested in that.
I think there's someone online who has an active microphone.
Were there any other products, Alejandro? Were there any other products that you were interested in? So rain rate, I think, is something we talked about early on. I'm not sure it's something that's easy to retrieve from ABI. I don't know if it will be, if there's a product that's planned for GeoXO. But so CSPP Geo is just starting to, this is the first year that we'll be working on anything under GeoXO funding. So, we'll be looking forward to maybe getting some newer GeoXO products out there. Yep.
Any other questions? Okay, thank you very much, Graeme. All right, for our final presentation of the session, originally, Kathy Strabala was intending to be here. Unfortunately, she was not able to make it, but she did go ahead and record her presentation. So we will play that for you now. So Kathy will be, her presentation title, Empowering Users to Create High-Quality Satellite Imagery with CSPP, Polar to Grid, and Geo to Grid, which both Liam and Graeme briefly covered in their presentations. And Kathy will be giving a more extensive presentation on some of the features of both of these software packages.
Hello, I'm Kathy Strabala. I'm sorry that I can't be with you there in person. I'm going to talk about Polar to Grid and Geo to Grid, which are part of the CSPP suites for Geo and LEO software. And my co-author is David Hayes, who's a software engineer. He's a very good software engineer, and he is, like I like to say, the brains of the operation. He's also part of the PyTroll team. And if you're not familiar with PyTroll, it's free and open source Python for processing of Earth observation satellite data. And the reason that is important is because these simple bash shell script interfaces that I'm going to describe are based on largely based on the SatPy library, the PyTroll SatPy library that is underneath. So the purpose of this software is to make it easy to create high quality images. So it's open source reprojection software packages that support the Linux operating system for polar orbiter and geostationary meteorological satellite data. The original creation of the Polar to Grid software, which is the first package that was created, was that we needed a tool that could run at polar orbiter direct broadcast antenna sites to create NetCDF3 from SUMI MPP VIIRS SDR files for display in the U.S. National Weather Forecast Office visualization tool, AWIPS. With the success of that, we extended the use cases to include more instruments, more spectral bands, more products, and output data formats. The popularity of Polar to Grid led to support for geostationary imagers through Geo to Grid, and the funding all comes through NOAA. So Polar to Grid is distributed through the CSPP LEO website, and Geo to Grid, it is distributed through the CSPP Geo website. The installation of Polar to Grid and Geo to Grid is very easy. You download a tarball, you unpack the tarball on your Linux server, you set an environment variable, and then you're ready to use the software. So when we look at these images, I always used to think the same thing. Why isn't it easy just to do this? It seems like it should be so easy. At one point in time or another, all of us who use satellite data are going to need to make a nice image. So that's what this software is trying to make it possible to do. So the creation of satellite imagery is complicated by the different types of input formats that they all exist in, the data storage characteristics, what the calibration, the geolocation, is it a science product, the swath type, the satellite projection, and the output format, which are largely dependent on what tools are used to display the end product. So using this data, the VIIRS data example, the VIIRS is the imager on board the JPSS suite of satellites. So this is a 5-granule set of VIIRS band 1 data that's displayed in satellite projection. So nothing has been done to the data, it's just displayed one granule after another. And what you can see is that in the middle of this swath, it looks like, I can see some pretty nice looking features. It looks like there's land and ocean and clouds in this image. But as I go to the edge of the scan, I notice that it looks like there's lines of missing data in there. This is the bow tie deletion region, which is not included in the downlink. It's not a problem with the data, it's a characteristic of the data that needs to be handled if you're going to make an image. And the way you handle that is to reproject the data onto a grid. So you spray this data onto a grid, and in the VIIRS data example, you put it onto a WGS84 projected grid, which is also the Google Earth projection, or also called CrIS. And so you can see that it gets rid of the bow tie deletion problem. But then the next step is that I want to display it, say, in my tool, which is the AWIPS Visualization and Analysis Toolkit. So to do that, I need to reformat the data into NetCDF. And once I've done that in the correct NetCDF format, it can be displayed then in my end user tool. So these steps are what Polar to Grid and Geo to Grid aim to make easy. So once you've downloaded and installed the software tarballs, then to execute the software is in the form of simple bash shell scripts. They interface to the underlying Python. So the main execution script for Polar to Grid is polar2grid.sh. Then you provide it with -r, which is the reader name. In this case, I'm looking at VIIRS STR data. Then I provide -w and the output data format product, which is GeoTIFF, and then -f, and then a path to the data. And if I point it at a data set that has all of the different bands and geolocation, I can, with this one execution, create all the bands. And I've made a montage of this particular data set that's from May 12, 2026. And if you have more than one consecutive granule, it will aggregate those granules as well. So in this case, I've created 5 I-band files, 16 M-band files, a day-night band image, as well as a true and false color image by default with that one execution. On the Geo2Grid side, it's very similar. The main execution script is called Geo2Grid-sh. It's the same format. I use a reader name. In this case, it's ABI level 1B. The output format I want to be GeoTIFF, and then -f and a path to the data. And if this GOES19 ABI data has all of the different bands located in that same directory, or if I provided the location, it will create all the bands it can, that it finds data for. And in this case, it found all the bands, along with true and false color creation from that one execution. So this is full disk it's creating. I've made a montage of all of the bands, but it's full disk, full resolution. Let's say that I don't want to create all of the bands, but I only want a subset of products to be created. Well, then you use the -p option as part of these executions and point to the different products explicitly that you would like to create. So in my first example with Geo2Grid, I'm using the reader for the FCI level 1C NetCDF files. I want to create a GeoTIFF output product. And then the products I want to create, -p, is the 0.6 micron visible reflectance band and a natural color band image. And then with Polar to Grid, the example that I'm using is for VIIRS STR. I want to create an I-band 1 reflectance image, M-band 16 brightness temperature image, and then a true color image. And that would be the execution that I would use. And I wanted to say something about these true and natural color RGB files that are created. The output images all go through these processes as part of the image creation process. So there's atmospheric correction to remove the effects of the Rayleigh scattering, sharpening to the highest band resolution, creation of the green band if necessary, for example, on the ABI imager, and then division by the cosine of the solar zenith angle, which then creates reflectance, actual reflectances that are used as part of RGB creation. So from those executions, it does all that to create the natural and true color products. So if I look at the Geo2Grid output from this command, from the FCI command, here's the 0.6 micron image that's created and the natural color image that's created from this 29 March 2006 data set at 12 UTC. Now, I also can define a grid or projection of my own if I don't like, for example, the projection that's used. And specifically, I'm talking about this in terms of Polar to Grid. So the default projection for Polar to Grid is WGS84, the Platt-Carré projection, and that's about 0.0057 degrees, so about 600 meters at the mid-latitude resolution. That's the default that it will create. Now, there's also some other projections that are predefined that you can use. What if I like Lambert conic conformal? There's predefined continental grids that can be used, for example, Europe and South America and North America. So the way that you can use that to override the default is to provide -G and then the name of that predefined grid as part of the polar to grid execution. You can also define your own grid. So if you want to do a specific region at a specific resolution that you want, we provide a script that helps users define a grid over a specified region. So that grid helper tool is called P2G grid helper.sh. So it can be used with either polar to grid or geo to grid. You can either provide a proj string using the -P option with this script. So if you're familiar with proj force string, you can use that. Otherwise, you can provide a grid name, the center, longitude, latitude, the pixel size in meters in the X and Y direction, and the number of pixels in the X and Y direction you want the output grid to be. So in my case, I wanted to create a grid over Germany centered on Darmstadt. So polar to grid helper.sh, Germany is the name of my grid. I want to name it Germany. 9.95 is my center latitude, 51.15 center longitude, 500 meter pixel resolution in the X and Y direction, 1500 by 1500 pixels. And I'm directing my output to this text file named myfcigrid.yaml. And the result of that execution is shown on the right, the definition of that grid that I've just, that's the grid definition that comes out of that execution. Now, if I want to use that grid in an polar to grid or geo to grid execution, this is how it would be done. So I would provide the name, the directory that this grid configuration file that I just created is located in. So that's the --grid-config, the location on my computer of the myfcigrid.yaml file. Then the grid in the file, there can be more than one of them that I want to use, in this case Germany, and then use that as part of my command. And in this case, I'm using, again, with geo to grid, the FCI level 1C reader. And the result of that is this image, which is a true color image that I just created, centered on Darmstadt. Now, you also notice that in that image I had overlays of boundaries and borders, so coastlines and borders, political boundaries. So there's another script that allows you to do that. It's called Add Coastlines. It's part of geo to grid and polar to grid. It has many different options so that you can control what kind of map you want, the resolution of that map. You can add color tables, annotate color tables. There's all kinds of options to it. I've used a pretty simple command, add coastlines.sh. I pointed it to my true color image that was made over my Germany domain, and I added coastlines, and I added in black, and I added borders, which are in white. Now, I can also do the same thing with polar to grid. I can use that grid just the way I showed using with geo to grid. I can also use it with polar to grid. So here's my execution pointing to the grid configs location. Again, myfcigrid.yaml. The grid is Germany. However, in this case, I'm doing something a little different. I don't have the data locally on my computer. I don't have direct broadcast data over Germany. So what I decided to do was point to the location of that data set on the JPSS marketplace, the Amazon marketplace cloud. So the S3 bucket I'm using, and as long as I know the location of those data sets, I can use it directly without having to download that data, having it locally. I can use it directly from the AWS cloud. Now, the command itself is pretty cumbersome. We're trying to make that easier so that people can not have to have the data locally. They can access the data directly from the cloud. But if I execute this command, it will create the image that I'm looking for. And this is the NOAA 21 VIIRS image from about that same time and location using that same grid. And if I compare it to the geo to grid image, you can see the difference in the clouds, not exactly the same time. The spatial resolution is different, and also the vantage points of the instruments are different. We try to make the software as efficient as possible. It has really good performance. It uses underneath the hood the DASC and X-array libraries. So we always try to keep benchmark tests done, timing the executions it takes to create all of the default images, which are all bands plus true and natural color RGBs. So users can also improve that speed by using more worker threads, using the --num-workers option. In this case, when I do the timing, I usually use 8. So for geo to grid, the ABI full disk sector, so full resolution, all bands, true and false color, takes about 2 minutes and 40 seconds on modern computers. For the continental US sector, takes about 40 seconds. Polar to grid version 3.2, a 10 granule daytime VIIRS overpass, which is a significant amount of data. Creation of all bands plus true and false color RGB products. It takes about 4 minutes and 23 seconds. So I'm going to talk about specifically polar to grid features now. The current capabilities of version 3.2 include SDR level 1 products, VIIRS, AVHR, MODIS, ATMS, AMSR2 GCOMW1, the Arctic Weather Satellite Microwave Radiometer, and the MERCI instruments on FY3D and FY3E. We also support a number of different science products, including a lot of VIIRS environmental data records, aerosol optical depth, the cloud products, surface reflectance, vegetation indices. ASCO EDR SSTs from VIIRS, MODIS, and AVHR, MIRS microwave retrievals from ATMS, AMSU, and MHS, HEAP NuCAPS retrievals from CrIS, ATMS, and IASI, AMSU, and VIIRS active fires, which you can overlay then on different images, and then AMSR2 gas level 2 products. And the next slide is an example of some of the direct broadcast products that we create from just some examples of polar to grid products that are created in real time from our antenna. So this is a true color image over North America from NOAA 2024. And another true color image that can be created using polar to grid is from the surface reflectance data, which is the next image, which is taking a while to show up. Oh, this is, I can't go back and forth. So you can see this has atmospheric correction to it. So you don't see any of the aerosols over the Great Lakes. There is fire and smoke in this image on the true color image. And this atmospherically corrected data set for the surface reflectance does not show that anymore. It's removed. And from then the surface reflectance products, you can do things like create the land surface, the normalized different vegetation index product, and that's what this looks like from polar to grid. And then from that you can create, not from that, but you can create also an aerosol optical depth product. Looks like this from that same data set. This is an example of a couple of the new cloud products that we support. So this is cloud top temperature and cloud top height EDRs. And you can see that there's, they're nicely color enhanced. There's a nice color bar, annotated color bar. So these are NOAA 21 products from last week. There's extensive example section available on the polar to grid documentation website that steps through how to create nice images from using different types of products and just working with VIIRS SDRs, for example. And then in example applications, we don't just like to do this, we like to make sure that it's useful. So this is a couple of examples of GCOMW1 microwave imager products. So on the left is the 183 gigahertz image. On the right is an 89 gigahertz image. So these are microwave imager images from taken from our own antenna. So these are over the central part of the United States from different wavelengths. But what's interesting about these, first of all, the different features that you can see, but also the color tables that are used are acquired or used from the U.S. Naval Research Lab site, which is sort of a standard among those people, especially tropical cyclone forecasters, who really want that. So we make sure that that's available in Polar Grid. And this is an example of an application of those products. So we work closely with the Guam National Weather Service. We have an antenna that we manage that's located on their facility in Guam. Guam is an island in the Western Pacific, and it's famous for this group because we were going to have a meeting there last year. So we didn't end up having. But they do have an antenna co-located with them at their forecast office. And the way that they transmit information to their citizenry on Guam is through Facebook Live broadcasts. So what I'm going to show is a 1-minute segment of a Facebook Live broadcast by Brandon Adlet, who is the meteorologist in charge at the National Weather Service office in Guam. And he gave this briefing about a forming typhoon that was expected to affect them, this Sinlaku. And using this microwave data, first of all, he was talking about the benefits of direct broadcast, and second of all, he was talking about the benefits of this microwave data in doing things like seeing through the clouds and locating the center of the cyclone.
Now, some imagery I want to show you. This is some polar orbiting satellite imagery that we received. We have a backyard receiver that, as we have these polar orbiting satellites orbiting over the horizon, we're pulling in real-time data here at the Weather Office. We're getting this data into our computers within 15 minutes, so very quickly. And what this information shows us is a satellite sensor that can look through the clouds. We're looking at the storm structure within the typhoon. And so on the left, we're looking at the lower level structure. Right over here, we see these arches, these little rings. That's indicating the eye of Typhoon Sinlaku is gradually starting to take shape. As we look higher up in the atmosphere, now we're looking at the more intense convection, the ice and the cloud tops. We're starting to see that same spiral, round curved banding that is indicative of a strengthening typhoon. And also, it shows you exactly where some of those heavy showers have been.
So Polar Grid, what are we working on now? We're working on Polar Grid version 3.3, which is going to add additional support for new VIIRS EDRs, including the CrIS products, the AMPS, which is the ozone mapper, level 2 products, including total ozone. We're adding support for the creation of different VIIRS RGBs, additional RGBs, and improving using data directly from the GWSAS marketplace. I mentioned that, and we're definitely going to work on improving that. And optimizations and bug fixes are things we always try to work on. And so here's an example of an AMPS level 2 image of AMPS total ozone. This was from an overpass last week. We're creating the level 2 products, and then Polar Grid supports it by creating the imagery. All right, if you move on to Geo2Grid now. The current capabilities of Geo2Grid version 1.3, which was just released last week, include GOES 16, 17, 18, 19, ABI, all sectors and modes, Himawari 8 and 9, 8HI, both HSD and Himawari cast, GeoComSat, the AMI instrument, FY4A and B, Agri instruments, Meteosat 12, FCI. And then as far as products are concerned, the ABR atmosphere products, including cloud products, aerosol, fog, and we also support land surface temperature. And then the GOES gridded geostationary lightning mapper products, especially the most popular one, which is the flash extent density out of that suite. And if we look at all of the different satellite sensor combinations that are now supported, the imagers, there's now 10 different ones. So the new version of Geo2Grid, version 1.3, supports a number of new RGBs for the ABI instruments. And there's 9 new ones. There's 9 different ones now. And if we create a montage of those 9, this is what they look like. And on the bottom right is the command that would be used to make all of these different product files. And if you look at then the combination of all of the level 1 products that can be created, there are now 27 different ones that that can be created by the level ABI level 1 input files. So one of the unique things about Geo2Grid that allows you to do is to create subsets using an option that is directly part of the Geo2Grid execution. So that option is, and the reason that that's possible with Geo2Grid is because geostationary imagers are on a fixed grid. So the option to do cutout subsets is to use the --LL-B box option, and then the longitude minimum, latitude minimum, longitude maximum, latitude maximum. So in this case, I'm doing a Geo2Grid command using the Agri FY4A reader, and I'm going to cut out the latitude longitudes that I've defined with this LLB box option, and I'm going to create the ash, dust, fog, and true color cutouts. And when I execute that command, this is what I end up with, these 4 RGBs. And that subset command can be used with any of the imagers. That Geo2Grid also supports a number of different product files. So for example, the AIT cloud top temperature product, this is an example of the command that I would use to create that with the -p temp, and then pointing to that AIT that can be created, the AIT cloud product file, which can be created either with AIT, or you can use the one directly from the NOAA archive. And it's already got a color enhancement. That's what this product looks like. And then one other thing that we can also do is overlay that on another GeoTIFF. So there's a script that's in Polar2Grid and Geo2Grid called overlay.sh, and allows you to overlay one GeoTIFF file on another one. In this case, I've decided to use the base as the true color image. This is a GO17 case. You can see California in the upper right. And then I'm overlaying on top of that cloud top temperature product that I just showed. And it's really a simple command, and it works really well. And then I can also do things like add a color table, using the add coastline scripts, and define it exactly the way I want to. So one of the advantages of geostationary satellites is the temporal resolution. And so an important feature to be able to do with geostationary imagery is be able to create animations. So we step you through how to create animations using Geo2Grid. And one of the things that we do to help that along is to provide a script that will take GeoTIFFs or PNG files, and create an animation from them. No matter how many they are, you can use, it's a very simple script, gtiff to mp4.sh, and then you can give it the name of the mp4 data set that you want to create, so the output file name format, the output file name, and then you can use wildcards, such as, the bottom line is my gtiff to mp4 command. I use wildcards, and that will create, using the star true color star.png, it will create in order an animation MP4 of all the true color files that it finds that are PNGs. And so in this case, I'm making some images of Hurricane Melissa, which ended up being catastrophic when it hit the island of Jamaica last year. It was catastrophic. And I'm creating an animation from 1 minute mesosector data, 15 UTC to 19 UTC from 28 October 2025. That consists of 239 different images. In this case, it's true color images from ABI 19. And then I'm going to show a second set of animations with a GLM, the GOES Lightning Mapper, flash extent density overlaid on top. So the instructions for this, step-by-step instructions, are part of the example section that I just showed. But I want to show the end result. So here, at first, I'm going to show the true color animation. One-minute imagery, it looks like a boiling pot. And then the next slide. is going to be one that has the GLM product, the flash density extent overlaid on top. So I created images of the flash density extent GLM for the same time periods that I had of the true color images that I made. And then I overlaid each one, and then I used that script to create an animation. Show it one more time. And I think it's interesting that once the hurricane comes on shore, that all the lightning flashes are essentially to the north of the eye. And of course, we don't create these images so that we can gawk at them. We create images so that we hope that it will prepare us in the future to, you know, save lives and property. And then I wanted to talk about one more geo-to-grid utility. We really want to make sure that these products, the products that we make with CSPP, GEO or LEO, it's extremely important to us that these have scientific integrity. We spend a lot of time on validating them, the images, the products, everything. And so here's an example of how the geo-to-grid image products are good enough for them to be able to be used in research. So in this case, this is an example of this group from the Philippines using geo-to-grid to create images that were used in their study of chlorophyll concentration of Laguna Lake using Himawari 8 satellite data. And that's the end of my presentation. Thank you very much.
Okay, if there are any questions, we will encourage you to follow up with Kathy. If anyone would like to obtain her email or have questions, you can reach out to any of the CSPP team and we can connect you with Kathy. But in her absence, we do thank her for her talk and we do wish she could have made it. So we are maybe just a couple minutes ahead. I think I see 3 minutes, but we'll just take a slightly longer break because we have hit the morning coffee break. So please be back here promptly at 11 o'clock to start our second morning session. Thank you very much. And finally, before we break, let's give one last round of applause for all of our presenters this morning.
All right, everyone, we're about ready to get started. So if you could please take your seats. There's Satya. So our first speaker for the second session is Satya Kalluri from NOAA, and he'll be talking about the evolution of NOAA low Earth orbiting satellites architecture and plans for direct broadcast capabilities.
Let's see. Good morning. Thank you, Graeme, for that introduction. I'm Satya Kalluri. I'm the chief scientist for the LEO program. I'm going to talk about a few things today. Here's the outline. First, I'm going to talk about the status of the current GWSAS satellites. Then talk about LEO, which is the low Earth orbit mission planning, where we are in terms of LEO in general, where we are headed, and where we would like to be. Where we want to go, where we'd like to be is very aspirational. Then there's a reality where we are and what we are trying to do. And then we'll end up with some summary, and hopefully we'll have a conversation. This is the present JPSS constellation. The Joint Polar System satellite consists of 5 satellites. SNPP, which is the prototype mission developed by NASA, launched in 2022, and it's, well, actually launched in 2011. So it finished more than 14 years in service, right? So these satellites are typically designed for 7 years mission life, but just like any good satellite, if you survive the first 3-4 years, then they last forever, right? So it's like mortality. If you survive till 20, then it's fairly high success that you'll survive till 50. And if you survive till 50, you could go up to 80. So having said that, SNPP was a prototype, and then we have NOAA 20, 21 in orbit. They're all in the same orbit, as you can see. The 21, which is the latest satellite, was launched in 2022. And 20 is launched in 17, is a secondary satellite. So what does the designation primary, secondary, and tertiary mean? So we have requirements for reliability and availability, and these metrics are assessed against the primary and secondary assets. So why do we need 2 satellites? This is what we call as 2 failures to a gap, meaning if the first satellite were to go into a storage mode or were to go in offline mode, then you still have a secondary asset, which is a hot backup, right? And when the secondary satellite also has an issue, or if you lose 2 satellites, then you have a gap. Otherwise, we are gap free. So there are some talk, there are maybe some plans to deorbit SNPP maybe in a year or so. It's a fluid situation. But at the same time, we are planning to launch the 3rd satellite in the CC series, JPSS-4, in 27. So we launch every 5 years, and the mission life is 7 years. So in theory, what it means is that you have at least a couple of years of overlap between each satellite to verify, validate, cross-calibrate between one mission to the other. The last one, GPSS-3, is the last satellite in the mission, expected to launch in 2032. It's already finished. It's in storage. Now you might ask, why are you launching JPSS-4 before JPSS-3? The reason is quite simple. The earlier satellites have the Earth Radiation Budget Sensor series, and NASA wanted a gap-free Earth radiation observation capability, so they built a series follow-on called Libera. And Libera is going to go on JPSS-4. So if you launched it on the third satellite or JPSS-3, then there would be a gap. So long story short, JPSS-4, once it is launched and successfully checked out, yeah, it will become the NOAA 22, right? So here are some beauty shots, pretty pictures. This is JPSS-3 and 4 finishing up. Both are in, the JPSS-4 is undergoing the environmental test. You can see on the right. JPSS-3 has completed its TVAC. It is already in storage, right? So again, 2027 is when we launch JPSS-4. What happens after JPSS, right? So we often hear the word a 3-orbit backbone. EUMETSAT operates the 930 backbone. We operate the 1330 backbone. And the US would like to also have a third backbone sometime in the early morning. This is the orbit that used to be held by DMSP. DMSP is the DoD mission. It has a microwave imager and sounder. It is replaced by a different mission called the Weather Service Follow-On. It is only have microwave imaging but no sounding capability. So in that vein, given historically how long it took to build these satellites, how long it takes to get it approved, launched, and commissioned, we wanted to have a early leg up on planning of the JPSS mission, and we formulated what is called as the LEO Neon program. Before I get to that, so here is the LEO flyout chart. So what you have on the top are the JPSS mission, which will go on according to what you see here and based on how long the satellites last, well into mid 40s, right? Touch wood. At the same time, as you heard yesterday, and again from Liam's talk, the legacy post satellites, NOAA 15, 18, 19, have been decommissioned, and they are no longer providing data. At the bottom is the METOP B and C will be replaced by METOP SG, which is successfully launched. So the main takeaway is the top line, the 1330 orbit, the METOP line, the third line have a very, very well-established, credible, long timeline of launch and operations. Meanwhile, we also heard from Silvio Canistri yesterday the plans for the Arctic Weather Satellite, or STERNA, right? The Arctic Weather Satellite is going to boost up the capability of microwave soundings. And we are all focused on microwave soundings because that's the observation that is the most paramount and important for the models, right? Whether it is the National Weather Service, GFS, or the European ECMWF, or the Met Office model, or the JMA model that we have seen yesterday, or the KMA model, or the CMA model, right? The microwaves are the one that drives it. I'm not saying that the IR is less important or the scatter emitters are less important, but if you look at where you get the biggest bang for the buck, it is typically microwave, and several studies have demonstrated that the value of microwave hasn't diminished. The more you add, they haven't seen a saturation, right? So there you go. We are going into what is called the disaggregated architecture. What does that mean? For example, when we were walking around the very nice EUMETSAT campus here, we saw the METOP B and C spacecraft, and each one is the size of a small pickup truck or a minivan, all right? And they're very complex. It takes more than 10 to 12 years to build. It has more than 4 or sometimes 5 types of payloads or sensors. Each one takes 7-8 years to build, and if one is delayed, then the whole mission gets delayed. They are expensive to build, they are expensive to integrate and launch. So in the disaggregated architecture, we plan to have individual satellites with each satellite flying a sensor. Like one could have a microwave constellation. So we're going to launch them in series. Each series will have a bunch of observations like microwave, IR, multi-purpose imagery, and you could be building 5 or 6 microwave sounders that you could launch whenever you want to launch. That makes it agile. So where you're building the microwave fleet, you could in parallel be building the IR fleet. You could also be building a imager fleet, right? And there are no dependencies on one should launch when the others are ready, or they all have to be integrated at the same time. So the main tenet of this is you get architecture that is flexible, agile, and resilient here. That new program that we have under LEO is the NEON. It stands for the Near Earth Observation Network, right? And it plans to have a mission life of 3 to 4 years. These are small spacecraft buses with single instruments, like I mentioned. There are a couple advantages out there in the industry. There is a catalog of small satellites, right? Many vendors are building them. So if you go to any of your favorite factory vendor, whether it is Northrop or Airbus or anywhere, you have a massive number of crew working on a big METOP type satellites. It'll take months, if not years, to build. And you go to a small satellite production, it's like a car assembly, right? They're building 10 a day, right? All they need to do is figure out the size, weight, and power, or the communication that you want. And then you say, yep, I'm going to buy 3 of these and see if your spacecraft can accommodate the sensor that you want. We're not talking about CubeSats here, right? Not a 3U, 4U, 5U. We're talking about small spacecraft. So there are some economies of scale when you go to this paradigm. And in the low Earth orbit observations, we wanted to take a holistic look at all types of Earth observations that we can do, and we do now in low Earth orbit, and put them into different categories of observation types, such as multi-purpose imagery. Examples are VIIRS, MetImage, BODIS, the old AVHR, and so on. The UV measurements are atmospheric composition measurements. They are include the arms that we have. Then there's a GOLB. Then TROPOMI, Sentinel-5. So that is the UV near-IR suite of sensors. Then the soundings includes both microwave as well as IR. These are like AMSU, ATMS, MWS, YASI, YASI-NG, and so on. And then you have the altimeters, then the synthetic aperture radars, the scatterometers, microwave imagery, as well as the LiDAR, right? And all these types of measurements go towards addressing the 5 major areas within NOAA. This is the Weather Service, the Weather Ready Nation. Then there is the oceans, fisheries, and marine weather, and some climate there, right? So the other important thing is we as a organization, NOAA, do not build everything and operate every type of sensor. We historically rely on you, represented by various organizations, whether it is EUMETSAT or ESA or NASA or CNES, So that's where the partnerships come in. We are powerful together as a global community of Earth observing satellite operators. Imagine if everyone were to launch all these satellites, right? It becomes not a challenge, but also a big financial burden, right? So the spirit of open data sharing and partnerships are central to our tenet for LEO. So we buy and partner. Buy is a new paradigm that in the US we have been directed to look at. There is a very strong and a healthy commercial market that has seen emergence in the US, especially the microwave sounding. There has been a very good market for very high resolution imagery, especially for defense applications, land use, land cover, urban planning at 1 foot, 3 foot, 1 meter imagery. But we're not in that business, right? We are looking at synoptic observations, as you see. We don't do anything finer than 400 meters, 375 meters, right? But there is a very strong emerging market out there for microwave, and radio occultation has been established for almost a decade now. So we will buy what is available if it suits our needs, and we will partner where we can. So we have a joint polar system agreement with EUMETSAT. We do the 1330, they do the 930. We also have a good partnership with the Space Force or the Air Force or Department of Defense. They do the microwave imagery. And we do leverage what others are doing from NASA and ESA with the Sentinels and Earth observing missions. But the core observations that really are needed for NWP models like soundings, we feel that at least for those backbone missions, we need to do on our own. So this is the LEO architecture plan. As I mentioned, 3 hybrid sun synchronous platforms to meet the user's need. Ideally, we would like to have all 3 depending upon the budget. So at a minimum, we are planning to do continuity in the 1330. We are aiming to get a global refresh of 4 hours. You get a global 4-hour refresh if you have 3 orbits. Now, as you know, from a polar orbiter, the higher latitudes, you have more frequent requests. There are gaps in the equator, low latitudes. So ideally, you would like to have 6-hour separation that will give you 4-hour refresh. So these are the primary observations, as I mentioned, JPSS and 130 EUMETSAT. And in the 530, we could launch, we are planning to launch a satellite called the Quick Sounder. I'll talk about it. And maybe also look at some commercial opportunities to fill it in. And there is also some data available from private sector to look at inclined orbits as well. ECNWF did a study a couple of years back looking at different architectures, inclined orbits versus polar orbits and combination of those two. And they said polar is what we know, but inclined can also help as well. So this is the type of exercises we are doing. If you want to pursue 3 orbits, and if you want to have 6 hours, 4 hours, 2 hours, how many satellites do you need? So on the left here, for example, okay, it doesn't work. So the 2-plan constellation, as you would see, would result in gaps at the equators. The equatorial regions, as you know, are very important because that's where majority of the hurricanes and tropical cyclones form, right? And the gaps become narrower if you have a 3-plane backbone. And if you have 6 planes, it almost becomes totally gap-free. And at the bottom, you see a table that's showing the refresh rate that you get for 2-plane, 3-plane, and 6-plane. So if I have a 3-plane backbone at 6-hour refresh, I get 97% of the Earth covered, and that's what we are aiming. If I have only 2 planes, that only covers 81% of the Earth. Again, this is another eye chart, how you would put these orbits and what type of coverage you would get. This is specific to microwave, but it can be extended to any observation as well, as long as you maintain a typical swath of 22 to 2,500 kilometers. Okay, what does it mean for the direct broadcast community, right? Right now, we have a limited set of LEO satellites. As Liam was talking today, and his poster showed, you need to schedule your antennas to receive all this data. Imagine I proliferate the constellation with 20 different satellites, right? You need more than one antenna, it becomes expensive, and it would result in conflicts, right? You'll probably be in a situation where you have to pick and choose. So one thing we are exploring is 3 layers of communication. This concept of satellite to satellite, inter-satellite data relay through laser comm is being demonstrated experimentally, and not on the civilian side operationally, but there are other agencies out there. So what you see here in this cool animation is you have a satellite with a laser comm. The yellow dots are a low Earth constellation of communication satellites. And as you fly your Earth observing satellite, in this case, notionally, you can look at a Starlink constellation or an Amazon constellation. And these are your touch points. As you see them in the limb, you use your satellite laser comm to broadcast and talk to this satellite, which would receive your data. And these communication satellites, that's all they do, right? They're communication satellites like your Starlink. They would have their ground network that feeds into some cloud, and you would get the data, right? So you're continuously collecting the data, looking for a touch point in space for opportunity, you broadcast the data, and then you keep going until you see another target, and then you send the data to that. In addition to that, we also plan to have the traditional RF contacts over the poles, X-band. For example, it could be Svalbard at KSAT, it could be the NOAA antennas at McMurdo to store the mission data, or they dump the stored mission data, or SMD, just like we do with the GWSAS and NetOp. And the third layer would also be a direct broadcast X-band that would bring down the latency to less than 15 minutes, one way or the other, right? So this is what we envision. We hope to the next generation NEON satellites would have something like this. So there are 3 layers of comm, 3 layers of redundancy. And as I said, the first thing we are looking at the microwave sounding. In the microwave sounding, we are going with a sensor called SIMBA, which stands for Sounding for Microwave-Based Applications. We are targeting hyperspectral microwave. Studies have demonstrated the benefits of hyperspectral in space from microwave to improve vertical resolution of temperature water vapor, especially in the boundary layer. And more than that, when you have hyperspectral, it gives you a choice to pick and choose those frequencies that are not contaminated by radio frequency interference from 5G, 4G, 6G, 10G, whatever is out there. Then there is also the opportunity we use a hyperspectral sensor as a inter-satellite calibrator. So you would do everything you would normally do for a backbone observation on the ground. For example, in the US, we use NIST standards, National Institutes of Standards and Technology. And once it is well calibrated, that becomes the reference, right? So right now, ATMS is the reference. ATMS has the same heritage channels that other sensors do. But if it is microwave, then you can have the luxury of picking those channels that a new sensor has. And the 50 gigahertz, 118 gigahertz will be there for temperature sounding, and we plan to have 3 to 5 year lifespan. Then here is a example of what we are aiming at. The request for proposal is out there. So the vendors are probably busy writing proposals. Now, hyperspectral is an emerging technology. So we are yet to learn a lot, just like when the first VIIRS sensor went up for IR. How many channels, and do you need to aggregate? Do you need to go principal components? How do you beat down noise? What is the stability? Things like that. Anyway, here is the hyperspectral capability that I talked about. Then there's a quick sounder. What is quick sounder? We have a spare ATMS that was in the factory. This predates the first ATMS built with SNPP. We did some minimal refresh. It was space-worthy. So we made a whole mission out of a spare ATMS. The concept here is that we would give the sensor to a vendor. The vendor is Southwest Research Institute, and then say, okay, you put it on a spacecraft and we launch it, and you use your ground stations and you give us the data, right? This mission does not have direct broadcast, so they are going to rely on KSAT ground. They think that you need at least 40 contacts per day or 3 downlinks to get the refresh latency down to what we have with GWSAS. Right now, they are looking at 3 satellites, 3 ground stations, but they plan to go up to 11. So what you see here are the yellow ones are where the commercial ground stations are. Yeah. So the plan is to take this data. So the vendor has a responsibility to command, control, downlink the data, put it on an Amazon cloud bucket, and we would just get the data, right? So we won't be in the business of command, control, operate the satellite. We'll just get the data. We have never done this before, so this is a Pathfinder exercise. And then this is the Sternus constellation. We're all excited about it. Silvio gave a talk. It will have many satellites and 3 different orbital planes flying between GWSAS and ATMS. So we are building an antenna farm called Penguin and McMurdo to work with EUMETSAT to bring down the latency. It will have direct broadcast, and Liam showed some pretty pictures of that direct broadcast. So with Penguin, METOP, GWSAS, commercial, and so on, I think we'll have a very healthy, robust microwave constellation. So in summary, we are moving towards a disaggregated hybrid architecture. Some we will build, some we will buy, and where there are opportunities, we will partner. The future constellations will have direct broadcast, except for a quick sounder, which is like an experiment to look at a variety of things. And we're also working with EUMETSAT to build the ground stations in McMurdo for Penguin. So there you go. Thank you.
Thank you, Satya. Are there any questions?
Yep, one in the back.
Are there advantages or disadvantages to decoupling the instruments in regards to data uplink?
So if I hear it correctly, what are the disadvantages of having a multi-plane disaggregated architecture? There are many, right? Nobody ever said it's going to be cheap, right? Because you're constantly building, launching, refreshing, and then, as I mentioned, if you have a swarm of these satellites, for those who are planning to have direct link, it is going to be a challenge, right? How many antennas are you going to have at your single location? So that's why data sharing as a consortia becomes important, right? Then there is, but the advantage we feel is that it provides the agility to build and launch when you need. From a programmatic perspective, there are also, we are government, right? So nothing is easy. How do you do an acquisition where every 3 years, 4 years, 5 years, you're putting one RFP after RFP and a bid after bid? How long do you choose? How long do you take? How long do you take to build? So at least in the US, on the NASA side, you probably if you follow the news, there is a lot of push to do things quickly, not take 2 years to select a vendor and 5 years to build and 10 years to launch, and, right? A lot of impatience. Let's build and launch and build and launch and build and launch. The other thing is when I speak with the weather community, when I say the weather, the modeling community, they would rather have 3 or 4 good, well-calibrated, solid, stable platforms than 15, 20 small, cheap satellites, because it takes them 4 to 5 months to do bias correction, calibrate, validate. And once you ingest the data, the mission might be over, right? So they don't want to be always in the catch-up mode. But we'll see. Some people say, hey, if you use AI, right, it problem solve, but who knows? Yeah, we are in the frontier of new territory, right? Some might work, some might not work. But the good thing is we have enough resiliency out there and redundancy, and this is the right time to go experiment.
Antoine?
Yeah, so regarding the SMBA small sat program, you mentioned that it will put pressure on the existing ground station because you have limited capacity to acquire so many new satellites, especially if the model now is going into smaller satellites that are more numerous. Do you have an idea already of how many satellites are being planned? So you mentioned the NEON program for the sounding, and maybe some other one as well. So is there an overall number of small sat that are planned?
Good question. So there are 2 facets to this thing. Then there is the architecture that you have seen, right? I would like to have a constellation of microwave, a constellation of IR, a constellation of imager, and other communities say, like, where is my atmosphere composition, kind of a thing, right? And if you look at the priorities, microwave comes to be in the top. Then you say, so if I'm building a 4-year satellite, then ideally I would like to go build 6 satellites at once, right? And when I'm doing that, well, why not I go build 6 in parallel for IR? And oh, by the way, I'd like to buy it in batches. The first batch will have A capability and second batch will have improved capability. But the reality is the budgets won't let us do that. When we go up to our Congress and ask for money, the first thing they're saying is, boy, you already have 3 satellites up there and you still have 2 on the ground. Why are you asking for more? Right? It's hard to explain. Then just like you guys in Europe, we have to say, if I launch 2 of these satellites, how much money are you saving? Is the hurricane track going to be improved by 50%? What is the return on investment? I hate to say this, but that economic analysis is voodoo science. It's not pure scientific where you put data and sometimes it works, sometimes it doesn't work, right? So how many satellites? The honest answer is it depends on the budget. And it also depends on how healthy your current satellite constellation is, right? Yeah, you ask me in 3 months, I'll give you a different answer, right? What we gave an answer in January is very different now what we're giving, right? That's the budget reality. Thank you.
All right, thank you, Satya. I think there were other questions, but please find Satya at the break.
Yep.
We need to move on to the next speaker. So,
Thank you.
Thank you. Our next speaker is also from NOAA, is Lihang Zhou. And Lihang will be talking about NOAA LEO products, updates for CSPP users.
Good morning, everyone. Thank you for the opportunity to provide data LEO program data update for the CSPP users. I want to start first acknowledge my co-authors here, such as here, but also many more, because these days to provide reliable, high-quality operational product to our user community, it's really take mission, science, and operation all work together, so it's teamwork. Here's a brief agenda. So Satya already gave a very nice mission updates. So for GWSAS, our next launch will be September 1st next year, GWSAS 4. And then GWSAS 3 is in long-term storage with a planned launch date late in 2032. And now we have NOAA 21 as primary, NOAA 20 SMPP, each produce more than 60 products. So there's a lot of good GWSAS operational products there. And specifically, I want to mention there's also science upgrade ongoing. I want to specifically mention the NOAA 20 OMS high resolution implementation happened recently, which we directly benefits from the feedback from our direct broadcast user community. And QuickSounder, as I mentioned, we have a launch date now, February 15, 2027. So we plan to produce a similar product like ATMS and EDR, snowfall rate, and VIIRS product from QuickSounder. And the next will be a Neon Series 1 Simba. The RFP released last month, and the launch date, national launch date is mid-2030s. So all the J4 instruments are now implemented on the spacecraft. You can see all the current ATMS, OMS, and the VIIRS, CrIS, and then there's a Libra, the radiation budget instrument by NASA, also will be on GWSAS 4. So here's a summary of the delta of the GWSAS 4 compared with the GWSAS 2. So as mentioned, the Libra will be a new sensor on board J4. And so very similar instrument, but the GWSAS 4 VIIRS implemented will implement faster scan rate to correct the scan-to-scan underlap in J1, J2. I believe that software already implemented in operation software and also in the latest ADL. I believe it's also in the latest CSPP package already. And GWSAS 4, also there's enhancement of especially the spectrum extended to cover beyond the current spectrum beyond 380 all the way to 440. So that provide more accurate NO2 and air quality monitoring capability. And there's a code change and the lookup table update for that for J4. So here's a summary of the J4 algorithm and the Kava readiness. All the pre-launch PCT lookup table updates are expected to be completed June 26. Actually, I believe all the sensor lookup table already update already delivered by Assist to Assist, and then the ARMS J4 upgrade we mentioned in previous slide that expected to deliver June 26. After that, it's a 3 months, June to September time period. It's pre-launch testing, end-to-end testing events. And the proxy data will be generated for J4 for EDR testing in September timeframe. And then the ICBS is also setting up to get ready for the pre-launch testing. So for all the GPS's product, we go through very careful carve-out process. And this is a J4 plan for the carve-out activity. It's based on the NOAA 20 and 21, but even accelerate. I could see those green highlights are even faster timeline compared with the GPSS2. So this is J2 and J4. As you could see that there's some more accelerate timeline for the J4 carve-out activity. Sorry. Right. So next few slides, I'm going to talk about some of the R2O of the new LEO product. I heard some of those probably mentioned in previous days, but you can see this is a brief list of new product. In addition of the original requirement, the original product size define the level 1 requirement. So for atmosphere, there's ALPW and derived product, as well as VIIRS PM 2.5. And there's a suite of the land product like Live Area Index, BRDF, and enhance the vegetation health and high resolution soil moisture. I should add here also we are bringing the VIIRS downscaling flat product into the operation as well. You will hear from Sammy probably later in the later talk. And then for ocean, we have a blended SST product. And cryosphere, I heard a lot of good use cases of the ice product. So we are bringing blended ice motion and also enhanced resolution sea ice into operation. And there's a increasing upgrade and uses of AI machine learning algorithms, including the microwave imagery. And also there's new missions like AWS. On the right is an example showing that AWS with additional higher frequency channel, you can see the improvement of the soil moisture sounding. With and without this higher frequency channels, you could see the improvement of the water vapor sounding from the VIIRS algorithm. So I think Liam showed a snowfall rate example, but this is AMS time, late January this year. Significant snowstorm span across the United States, reached, you can see here, like Texas and even Alabama, where not usually you see this. So this is a snowfall rate product generated from more than 10 LEO satellites, and then blended together, showing the, it can capture this very fast evolving events very accurately. And the AWS is also part of the VIIRS algorithm. It's in process to implement it in GINA, and as well as the snowfall rate and VIIRS from the AWS. So this is just to give example that the snowfall rate product benefit from the direct broadcast processing. So thanks to the CSPP team provide the data, direct broadcast data, and the snowfall rate team actually set up the direct broadcast website in University of Maryland. On the right, you could see the comparison of the latency. The direct broadcast snowfall rate latency is significantly improved, then the operational product generally less than 30 minutes, especially for ATMS, is less than 20 minutes. So this is really a very impactful new product, the ALPW. The picture taken is when Satya and I visited the WPC, showing that they're using this product in operation. This is a very good example of the development that CIRA developed this product used by the weather forecast users, and they really want it, and then we bring it to operation. So a very nice R2O example. Here's a very important use case for this product. So last year in Texas, there's a significant flooding disaster event, devastating disaster. But because it's advective layer piece of water, it can give like 1 to 2 hours ahead of time for nowcasting. So it's actually used by the WPC when they issue a warning for this event. So they did mention that in their discussion. And showing here, you can see the heavy moisture flow from both Pacific and also Gulf of America, all emerging to the region. And the lower panel showing the VIIRS product also showing very heavy and deep moisture level. So I also hear a question about SST. From this, we have the LEO SST VIIRS have near real-time product. But this is showing that the latest product combining the morning and afternoon SST product from MetUp and the GWSAS. As you can see in the center, that's a daily product with a very nice coverage and gap filled for comparatives only use AM, OPM. Some of the land product, like leaf area index, was not in the original level 1 requirement, but we received the request from our National Weather Service users. So we brought that in operation already, as well as the BRDF. Those products really help the modeling for the forecasting, including the land surface modeling, as well as atmospheric air quality monitoring. So this is the BRDF in use by the NWS. This is actually ARL using the BRDF to improve the air quality, the dust drag forecasting, and reduce the forecast error in their operations, in their applications. We learned very good use cases of the ICE product. So here we are bringing enhanced the spatial resolution CIs for AMSR 3 should be. This is actually developed by University of Wisconsin CIMSS. As you can see, the improved spatial resolution AMSR product showing a lot of detailed CI structure. So the original is more like 6.5 kilometer resolution. The enhanced product will be more like 3 kilometer resolution. So talk about the AI. This is just an example. I was so impressed to see there's users of direct broadcast using the new caps these days in your operation. So this is one of the AI approach we are looking into. As you can see, it goes mad as AI. So the AI machine learning algorithm improve the spatial resolution as well as the coverage, and the accuracy is also improved compared with the current new caps based on the current assessment. So very promising algorithm. This is just the example that on the left is the MIDAS results. In the middle of the new caps, you can see that this is for the atmospheric river. The MIDAS capture it very, very nicely and without those cloud gaps. and compare really well with the model like ERA5 as well as GFS. So we are very careful and we're still evaluating the product performance. Also want to mention the important GWSAS GWMSR3 measurement. This is a continuity. You hear that MSR2 is currently being provided from CSPP. So for MSR3, it's going to be a very similar product, but there's also added channel like 10.25 for improved RFI detection and higher frequency channel 165 and 183 for the snowfall rate and precipitation moisture profiling improvement. So this is our schedule for the MSR3 product validation. The beta already done successfully by the Star Science team. We are expecting a provisional review in the summer and get ready for operation. The validated maturity will be next year. So this is early results showing in the beta review. As you can see on the right is MSR3 beta result for the run rate. Compare with on the left is the current operational MSR2 product. And they agree really well. So the initial results looks great. So I want to share with you some of the planning for transition MSR2 to MSR3 NOAA unique product. There's a lot of wording here, but basically we have 2 months, very tight window to transition from MSR2 to MSR3 because the MSR3 product will be declared in operation by JAXA end of June, early July, and then there will be 2 months parallel operation of MSR2 and MSR3. And then end of August time, the MSR2 operational data flow will be stopped. But the good news for dual broadcast users is that the dual broadcast will continue for MSR2. So you will receive both MSR2 and MSR3. There are probably some planning there, like you're going to get more data and you know how to set up your antenna, things like that. Some upcoming milestone, we received the MSR3 level 1 software version 1.0, but we're told that it's not operational, it's not a public releasable version. So version 1.1 is going to be delivered to NOAA from JAXA end of June, early July. And then our target operation for MSR3 NOAA product is August 2026 to be consistent with GWSAS GW parallel operation plan with the GCOM. Our assist team is work closely with our science team to make it happen. So UMSAT partnership is critical for NOAA. On the left is the current status of the MATLAB UMSAT satellite mission status from the UMSAT website. We are very excited to work with MATLAB 2nd Gen A1 data, and thanks to UMSAT providers early data. So the CAVAL efforts has started. Satya hosted a very nice workshop on the exchange the early CAVAL result between NOAA and UMSAT. And I believe those results were presented by the NOAA scientists were very appreciated by the UMSAT teams. And there's also good progress made by the OCS and OSPO team for system integration. So currently the NCCF is receiving RO data and MWS data as well. And we have planned to transition the NOAA enterprise algorithm into operation as well. So also want to quickly mention about the commercial data. So this is from Tomorrow.io on the right, and without Tomorrow.io is on the left. You could see that it covered some of the gaps of the operational mission by leveraging the commercial data. So Satya showed this earlier, but basically this is what we are targeting for the LEO microwave readings measurement. On the left, there's a lot of wording there. On the right, it's a simple version, kind of color-coded. You can see that our baseline, GWSAS and Lihang, SIMBA, in the purple color, like 130 orbit, and then EUMETSAT mission, METAP and the METAP second gen is in yellow, and green is Asterna, and then the blue one is commercial or possible Lihang as well. So that's a 5:30 early morning orbit. So with that, we are targeting 2-hour global revisit rate, cover 80% of the global. And for Alaska, it means like 1 hour. So it's really 1 hour global rate, so refresh rate. So that's really like a geostationary observation over the polar region. So a lot of opportunities of data and a lot of challenges that we, as a community, we need to work together. So here comes my summary. So for LEO, we're very lucky to have a very well-established science end-to-end science program. The current operation products running provide excellent product, and there's a science enhancement and systems ongoing for the new mission, as well as the science improvement of the current product. And we are in the stage of planning for the product for the future Lihang mission. We continue to support the direct broadcast user community. For the LEO, we work with the University of Wisconsin and provide operational algorithm to run the CSPP, and also plan to the next generation LEO missions. We thank all the feedback we get from the direct broadcast community. With that, that's all. Thank you.
Thank you, Lihang. Are there any questions?
Yeah, thank you for the presentation. You had in your slides the quick sounder launch this year. I remember from the previous presentation, there is no direct broadcast for the quick sounder. And I wonder as well, you have no user package plan as well. Do you plan to release, any software package for user? How is the dissemination plan for the quick sounder satellite, if you know?
Very good question. So the objective of the quick sounder mission is really to demonstrate the capability that we can launch to desired orbit in a very compressed schedule. So direct broadcast was not on that, but the data will be available through the cloud. I don't know if you heard about NOD. That's a NOAA open data dissemination. So it's the latency is really good. It's almost as quick as you see the operational product. So so the data will be available through the Amazon NOD, and the software and the coefficient and everything will be in classes. In the NOAA archive as well. So yeah, and we do have plan like Satya mentioned earlier for the direct broadcast or equivalent capability for the future Lihang mission. Thank you.
All right, any other questions?
What is the timeline for some of the level 2 algorithms for the METOP SGA1 instruments? The development of those, for instance, like porting some of the VIIRS algorithms to MetImage?
That's a great question. So the development of the METOP second gen has been ongoing in the past few years, and those are enterprise algorithms that basically leverage on the GWSAS algorithm and also can apply to the METOP second gen algorithm, METOP second gen A1. So the timeline is still being worked, but I think in the FY26, we are going to have more than 10 algorithms in transition to the operation. So it's going to be happening in near term. Thank you. And ask Priyanka, she's the one actually leading the effort transition the MATLAB second gen product and to operation. She's, I think she's somewhere. Yeah. Thanks, Priyanka.
Okay, if there are no more questions, thank you, Lihang, and we'll move on to our next speaker, who is Jessica Braun from SSEC CIMSS.
Thank you for the CSPP Leo team for their support.
Thanks, Lihang. Jess will be talking about GWSAS, that's how we pronounce it, GWSAS, and the use of CSPP Geo in supporting operations at NWS. Go ahead, Jess.
Thank you. I'd just like to say I thought I was being yelled at by my father being called Jessica. Okay, so just have a brief outline to talk about, and as Graeme said, we kind of call it GWSAS for reference. This is a NWS-based project. We'll talk about where SSEC comes into play, some of the processing components, how it's evolved over the last almost 7 years now, and then I'll follow up with some user examples. So the geostationary weather satellite antenna system, GWSAS, it's a network of antennas of GWSR series antennas. So to be able to get the current GWSR, GWS 16 through 19 satellites, as well as Himawari 8 and 9. There are antennas installed at 8 different National Weather Service sites. So these systems provide data directly from the direct broadcast data to the Advanced Weather Interactive Processing System, which is also known as AWIPS. And AWIPS is the main processing, display, and communication system that is used by the National Weather Service. So this is a list of the GWSAS sites. There are a couple forecast offices, one in Sand Lake, one that is Sand Lake, which is in Fairbanks, Alaska. There's also one at the very bottom that is in Guam. And then some of the other offices include the Aviation Weather Center, the National Hurricane Center, the Pacific Region Headquarters in Honolulu, Space Weather, Storm Prediction Center, and then NOAA's Center for Weather and Climate Prediction. So you'll note on the right of the table just has a list of the different systems, and you can see there's quite a large number of systems, and this is because it includes a prime, a backup, in many cases spares as well as individual test machines that our team at SSEC uses for testing and preparation for updates. And as of 2025, these are the current numbers as the NWS GWSAS project has moved and had a hardware refresh and moved to virtual machines. So how does SSEC come into play with this? We initially had a start of a contract support in 2019, and we were funded to initially develop an end-to-end system for processing and distribution of this direct broadcast data from the GWSR. So again, it's varied on the satellite because we've gone through some changes both on the GWS side and the Himawari with new satellites being launched over the last almost 7 years. And from the level 1 or level 2 in the case of the Lightning Mapper from the GWSR satellites, we take the data and it must be delivered via a local data manager. So it's called LDM. It's a utility that distributes data to NWS AWIP systems to the individual sites. And so in this case, we are creating some sectorized cloud and moisture imagery, which is a supported format for distribution into AWIPS. And then we also needed to prepare installation procedures. And so it was kind of a full design end-to-end processing that started in 2019. So we also support, so this is our ongoing maintenance support, the tier 2 team as a tier 3. So we are only an 8x5. while the tier 2 team is more of an on-call, more day-to-day routine operations. And so our job is to support them as 8x5 and then also train them on the current processing suite. When changes are made, we provide them with information and make sure that they are up to date on how the processing system works and that they have access to resources. And thankfully for us, this contract was just recently renewed in July of 2024 for up to additional 5 years. And as I said, we are just about to year 7. So what do we do? What is a tier 3 support? What exactly are those roles? So as I mentioned, we provide support to the tier 2 team. So we will work and provide updated software and procedures. We will support them if they reach out to us, if they are working on troubleshooting and having problems, if users report problems and they don't necessarily understand what the issue is, they will reach out to us and we will provide further assistance. We'll also support them with new feature creations based upon requests from some of the offices and the sites, as well as just keeping, routine, boring documentation up to date so that it is there and there for reference. But our role doesn't also only solely rely on the NWS and GWSAS. As I'll get to later, we use the CSPP-Geo software. We use a couple different packages. And so, in essence, we are also supporting the CSPP-Geo project in a way. And how do we do this? So we will be assisting and supporting them in the event that issues are found. So tier 2 could have a specific site, say space weather, and they reach out to the tier 2 and say, hey, the space weather data, like this isn't looking right. Can you guys look into this? We'll look at this. We'll then compare with systems that we have at SSEC. We may have, the CSPP Geo team may have had questions of this nature. And so we're able to utilize some of the GWSAS systems as also kind of a counterpoint in ensuring that if we are seeing an internal issue or an issue at the SSEC data center, we have another level of different antennas, different locations, different parts of the United States that we can compare with. And then on the flip side is we are also supporting with testing with packages, specifically the GRB package. If there are changes from the GOES-R ground system, with the current contract we have, the NWS, they will obviously want updated changes right away with significant time in order to update all of their systems. And so we will work with the CSPP Geo team to test out these patches and then work with the tier 2 team to implement these changes. And make sure that there are no impacts from any changes that impact the GRB data stream to the users and to the downstream VIIRS so that there's no loss of data, no loss of service to them. So this is a list of the personnel, and you might wonder why. Well, why does this matter? This is, contracted by the National Weather Service. Well, I'd like to point out the extensive list of the people who work on this project who are also part of the CSPPG project. So this is kind of a core, key element of why we have had so much success with this project and why we have a very good relationship with the GWSAS team and project and NOAA because National Weather Service, just because we work very closely and keep our hats separate, but at the same time, we're all working towards the same goal or ensuring, good software that is reliable, robust, and also, making sure that we are being very careful and efficient in providing updates to users when there might be an impact to something like the GRB data stream. Of course, I can also not acknowledge, go without acknowledging the core of our GWSAS project, which are our primary support staff, which both are here, Douglas Schumacher and Denny Hackle. I mean, without them, they are the day-to-day people who are doing the work. I can come up here and talk about it, but ultimately, they could give this talk significantly better than I ever could because they are the key to this project being successful. So what are the GWSAS components? So I mentioned we use CSPP Geo software. So we use the GRB package and the AXI tools, which is a utility package, and we use that specifically for the creation of the SCMI tiles. Again, these are the tiles that are created, submitted through the local data manager, and then be able to be ingested into AWIPS. In the very beginning, there were customized glue scripts, glue code. So there are scripts that manage and maintain the end-to-end processing. So starting with, for example, the GRB, ingesting the GRB software, the GRB data stream, creating the level 1 products, converting these products into SCMI tiles if required, handling the management of data storage, rotating logs, checking that all the processes are running, kind of like an end-to-end operational system. And so these scripts were kind of developed at the very beginning and have been modified and updated and just improved over time to improve efficiency and just make overall a better, more manageable and easier adaptable product. There's also separate glue code specifically for if you are looking for processing either the GOES-R ABI or the Himawari AHI data processing. So for the installation procedures, we work with the Tier 2 team because they do the actual installation. We are here solely as support, troubleshooting, assistance. So we're providing information like necessary prerequisites, so system configuration, what accounts, directories, storage, what specific packages might be needed in order to run our entire end-to-end processing suite, and list of other assumptions such as what are the IP addresses of each individual multicast feed. And then we also initially start with a set of step-by-step instructions for the installation of the different CSPP Geo software, the glue code, as well as a whole set of installation verification steps. Another key component is the customized environment setting. And this is my one mistake that I've found so far in the Tier 2 team, not the Tier 3. So this will allow the Tier 2 team to cater to each specific site. For example, Space Weather Prediction Center, they probably want space weather. Do they want ABI data? Well, that's up to them, but we can cater each specific site to exactly what data they want, what products they want. Do they want the SCMI tiles, or do they just want the NetCDF tiles, log retention, site-specific multicast feed addresses, as well as creation of the SUVI FITs. SUVI is the solar ultraviolet imager, so it's one of the instruments on the GOES-R satellites. And the FITs is a specific format. It's the flexible image transportation system, and it's mainly just used by the Space Weather Prediction Center. So that gives the option for it to be turned on specifically only, for example, the Space Weather Prediction Center. And again, the environment script is catered depending on if they are setting up a system for either ABI or AHI. So how has this evolved over the years? As I mentioned, the original design required just manual installation. So going through, installing the CSPP Geo software, the downloading and installing all the glue code, setting up cron tabs, setting up the environmental file, setting up the storage, where's the storage, log files, how long do you want everything retained. Some of that was in the environment script, but a lot of it was manual. So recently, a couple years ago, we completed a development of an automated installation script. And so it goes through just about the entire process, with the exception, of course, needing to set up the environment script. So it'll verify the prerequisites, and then it will fail. If it is missing a core component that is required, it will fail. And so this helps it be more efficient to avoid having, missing some of these requirements. I will download and install the latest versions of the GRB and the AXI tool package. I will download and install the glue code, and it will then also have verification and confirmation. And there are some additional verification steps. And again, it has that customizable environmental script. And so what is the difference? Well, one, I think we saw the number of machines at the very beginning. We're looking at, well over 40 systems. And so it's going to reduce the installation burden. Instead of having someone manually have to go through, I think it was a 22-page, when I looked, the old version was a 22-page installation step by step to copy, paste, or type it manually. So it's going to reduce mistakes as well, and it will also ensure consistency across every system. Just in case a step was missed or a step was done slightly differently, it's going to prevent all of these problems so that when there's troubleshooting, there's consistency across the board. There's also a reduction in time spent. So for any additional changes, minor updates for the glue code, when there's a new GRB software package released, or if there's a new Axie tools release, it will save a lot of time. And it also provides better adaptability for any GWSAS system changes, hardware refreshes. When the hardware refresh was done by the National Weather Service for the GWSAS project, the Tier 2 team and the NWS project manager and team lead they mentioned how much they really appreciated having the script and how much time it saved and how more efficient it was to get their new hardware set up and operational. Because as we know, once you are at end of life for systems, you have a little bit of pressure, or maybe a lot of pressure, to get to the new systems as soon as possible. So I'm going to actually talk about a little bit of Axie tools. And yes, this is still a CSPP Geo project, Geo package. But in the last couple of years, the GWSAS team had kind of discussed and decided, we could really use, an update to the original existing version of Axie tools. The original version was built before the creation of SatPy. The current needs have also changed with the release of additional software packages like the AIT framework. A lot of the options and features of Axie tools kind of became redundant, wasn't really necessary anymore for its original purpose. And in addition, it was not the easiest to be able to add new satellites, new features, new capabilities. And because of the contract that we have with the GWSAS project and the need for these SCMI tiles, we meaning the CSPP Geo team and the GWSAS team, we decided, we should work to pursuing an updated version. So the version 2 includes a rewrite that now does use the SatPy as its backend, some updated changes to the command line interface, as well as some additional changes so that we are now, officially compliant with AWIP's attributes. So, we kind of noticed some things during this development that, well, actually, the official AWIP's requirement documentation says, it needs, for example, just, an attribute limit of a number of characters. And so there were also some changes implemented to ensure that if anything happened, right now with AWIPs, that would actually be checking and failing. We're preventing future problems, future mistakes with this version. So now, while it is being tested and run in terms of official release through the CSPP Geo website, I did confer with Graeme. I could say this because I don't want to talk for him. We're looking for a release later this year in the third quarter of 2026. And of course, if you do have any questions on Axie tools, you can reach out to the CSPP Geo team, and I've put the CSPP Geo contact email there, and you will ironically probably hear from me. So can move on to something a little bit more interesting. Well, what are the benefits? Why do we care about our direct broadcast stations here, and how does this benefit users? So I have a couple examples that Graeme had obtained recently and was gracious enough to provide for me. So this is for an example from Pago Pago. So on the left, there's an image from the AWIP satellite broadcast network. So this is is distributed to different AWIPS sites and through AWIPS, and it comes from a network control facility. So it comes from kind of just a distributed feed. And as we can see on the left, it's clipped to only the northern hemisphere. And so there's only a small sector of, for in this example, band 13, covering their region. However, if we look on the image on the right, this is created from the direct broadcast antenna. And so this is GRB data. And so instead of having only band 13, they have all 16 bands and full disk coverage. And so it was reported by Eric Jacobson from the National Weather Service that they do heavily leverage this feed as it's really their only option for GOES 18 data for the Southern Hemisphere. In addition, with Himawari, a slightly similar situation. On the left side, the Himawari cloud data, so they have very high resolution tiles and it covers their immediate domain. But again, we don't have that full disk coverage. So through the Himawari cast, which is part of the GWSAS processing using the CSPP GeoAxi tools, while it is slightly lower resolution, it provides the global coverage and gives information about what's happening, to the south and the west. At the Hawaii Forecast Office, both GOES West and Himawari 9 at the time, the data is being used at the Hawaii Forecast Office, and for GOES West, it's also being used at the co-located Central Pacific Hurricane Center for higher resolution full disk monitoring. And on the right, again, and we can note, kind of the keywords, a full disk, so you're getting all the data, you're getting the full coverage to be able to help monitor for, more distant systems that could impact, and in this case, for the Hawaii Forecast Office, for any swell or marine potential impacts, as well as other possible impacts. And then the National Weather Service, Aviation Weather Service. So again, this is one of the 8 sites, and this was courtesy of Amanda Terberg. And the example on the right is a display from NAWIPS. So NAWIPS is just NCEP. So for NCEP, that is the National Centers for Environment Protection. So it is their version of AWIPS. So it's still AWIPS, it's just a slightly different modification of the AWIPS. And so this is an example showing geocolor imagery that was built off the GRB imagery from the direct broadcast antenna. And it was overlaid with METAR, flight category observations, IFR GAIRMETs, so it's ceiling and visibility forecasts, as well as the Aviation Weather Service forecast regions. And I see I put service there. That's my second mistake. And so she noted that this, is very heavily used at the ceiling and the visibility desk at the Aviation Weather Center. And so in summary, we were able to stand up and develop an end-to-end processing chain, that has been implemented at all 8 different National Weather Service offices that have direct broadcast antennas for either GOES-R, Himawari, or both, in the case of, for example, in Honolulu. And in terms of Honolulu, I'd just like to mention that there are also polar orbit antennas, and Douglas will be talking more about that tomorrow. Having, this close collaboration with a lot of shared team members on the CSPP Geo team has really benefited the project, because we have that inherent knowledge of the satellites, of the software, and the processing, and being able to collaborate together and suggest ideas of better ways to implement some of the processing that's being done. And again, the CSPP Geo software has been very robust, very stable, and again, almost 7 years and counting. And we like to think that our customers, and they have expressed that they are very happy with our service, and so we hope to continue this more. And so again, we meaning SSEC and myself, we feel that this value of this direct broadcast antennas really does provide significant value to these NWS offices, especially if they're was an upstream outage that has occurred in the past. And, you know, you never know what type of outages can occur, but, you know, if something occurs, you know, it impacted their other sorts of data, they will have an opportunity to just continue to utilize the direct broadcast feeds. So I will take any questions and thank you for your time.
Thanks, Jess. Are there any questions? All right, thank you, Jess. We do have a question from on Slido, not specific to you, but just a general question that I'll answer right now. The question was, could we have the presentations? And those are PowerPoint. So the plan, I believe, is to post the recordings that we're making of these presentations.
We will post the recordings after the meeting ends. And again, as I mentioned this morning, if there is anyone who would not like the recording posted, please reach out to us and let us know. We meaning being the CSPP organizing team, so Liam, Graeme, and myself. This is Jess. And then yes, also the PowerPoint and PDFs that have been uploaded that we are using, we will also post those to the website as well.
Okay, and our final presenter for the session is Mitch Goldberg from City College of New York. And Mitch will be presenting real-time MLP neural network atmospheric retrievals via direct broadcast, CSPP-compatible packages for ATMS-Only and combined CrIS ATMS VIIRS.
Thank
Please
you.
go ahead.
So does this work? Does the pointer work on this?
The pointer does not work.
Oh, okay. So I'll just say upper left. Anyway, thanks a lot for first of all hosting CSPP. You know, to UMetSat and also for the Wisconsin team for putting this all together. You know, I helped contribute to the development of CSPP, and but the part that I contributed mostly was calling it community instead of the NOAA satellite package. And the whole idea was to have the community get involved, not just using the data or using the products, but also contribute by providing algorithms. So now, after being at NOAA for almost 40 years, I have a new job as a professor at City College, New York. We have our own antenna, and now I'm contributing by developing algorithms for CSPP. And also hopefully working with the user community to get feedback. So this presentation is mostly not on a software package yet. It just shows the performance of the machine learning algorithms that we've developed for CrIS, CrIS and ATMS together, CrIS by itself, ATMS by itself, using VIIRS for cloud fraction, and also the plus, which was not in the original title, also generating retrievals from EASI and AWS. So here I am. This is my new playground, I guess. On the left is a nice picture of City College in New York. The building in the back, that gray building is the engineering building, which I reside on the 5th floor, overlooking Alexander Hamilton's house, and also looking at Yankee Stadium too. It's a nice location. That's our satellite dish. These are the people, part of my group now. So this is my 4th year starting June 1st. So we have 3 full-time research associates, 3 half-time or part-time, basically 1 day a week. And then a number of students being supported by, we have a NOAA program called EPP, Educational Partnership Program, that they provide stipends to us for, training students in NOAA relevant research. So we have a good group. So MLP, this is neural network. It's sort of complicated. People always say this is a black box. It's basically a set of knobs. If you think about these hidden layers, there's a set of knobs, and the knobs are first randomly adjusted through these different hidden layers that try to learn more and more about patterns. And then finally in the output layer, the input layer are the brightness temperatures. And, so I'll show you that later. The output layers are basically trying to predict temperature and water vapor, and we're using ERA5 as the truth. So you basically iterate around this. So the first time it's mostly random. These knobs, weights, where you're weighting all the input parameters called features, and then it compares it to the output, the truth, and then it says, oh yeah, I'm totally off base. Let me adjust the knobs again. Then it goes through again, and it takes iterations, and after 12 hours, you get something really good. So people call it a black box. I can understand why, but it seems to perform extremely well. And it's not really the complication is not really running it. The complication is really developing a really good training data set. So we use a single multi-output model design where all 37 pressure levels are predicted simultaneously. So so from that you get vertical consistency and so forth and efficiency. But let me show you what the code looks like. This is it. Basically, it's all libraries, and you just provided your Y's and X, right? What you're trying to predict, your predictors, your predictands, and then you run it, and 12 hours later, you produce the results. So it's like putting something in a slow cooker, but you have to make sure that the ingredients are really good, and that takes time. And so this part is relatively easy, putting together a training data set because you want to make it as diverse as possible. So neural networks, because they're called neurons, it's like the neurons of the brain. And so you have to you got to fill your brain with experiences, like the human brain, like you can recall things from, 10 years ago, 20 years ago, 30 years ago. So you have to be able to feed the model with as much information as possible. So these are the input features that we use for CrIS and ATMS and CRIS-Only and ATMS and AWS and IASI. The architecture, remember the slide that shows the different layers? We use more layers. At the bottom it says 256, 256, 128, 64. So we use more for the infrared, hyperspectral. It has more features. We use less features or less layers and features for, not features, less neurons and layers for ATMS, AWS, because it intrinsically has less information content. We also work in PC space for both CrIS and IASI. We have additional predictors like secant theta -1 that takes care of the limb effect, and land sea mass and surface pressure to help with high terrain and things like that. And similar for water vapor, very, very similar. And then we also derive these extra parameters, skin temperature, TPW, total precipitable water, cloud liquid water, and total column rainwater, which is like a proxy for precipitation from ERA5. And so here's the construction of the training data set. So the results that I'll show you, except for AWS because it's pretty recent, but the results for CrIS and ATMS will be, the training was generated from 2019 and being applied to 2025 and 2026. CrIS and ATMS, as you know, are very stable instruments, high performing instruments that you just have to pick 1 year. And that should be adequate for any period of time before or after. So the first thing we do is we actually we work in PC space. So we take CrIS data every day from 2019, but every 12th granule. The data's in 6-minute granules, 240 granules per day. So that's about 2 terabytes of data. And we convert that we use that to generate eigenvectors, 150 global eigenvectors. And then we go back to the original data. And as we're downloading the data, we transform them into PC space. And then we throw out the original data to, so the size is a lot smaller. Basically, the size of the data is about, 8% of the full size. So it's a very small data set. We're only using long wave and mid wave. We're not using short wave. I didn't want to get into complication of day versus night. And also, I want to use this algorithm as a proxy for GeoXO hyperspectral, which only has long wave and mid wave. Okay, so once I get my CrIS 150 PCs, then I have another data set, which is also at NASA, which is it's an algorithm from UW that runs in the NASA system that basically takes the VIIRS pixels, which for each pixel, you know the cloud fraction, and it aggregates those pixels into the CrIS footprint, and now I have a cloud fraction at the CrIS field of view. That's really important because when we do all sky retrievals and infrared, you have to know how much cloud is in the field of view. So that's an important part. Then once we add that, then we add ATMS, and here we're taking back as Goldberg, like remapping, and we remap ATMS to the CrIS FOVs. And now, then we add ERA5 reanalysis, temporally and spatially interpolated. So that's a lot of work. That took about 3 weeks of putting stuff together. So that's why I'm saying that this is the hard part. Once you have it, doing the machine learning is easy. All right. And then these are diagnostic plots. So these are things that I imagine that think about this data being processed through CSPP, direct broadcast. So the first thing you do is you take the CrIS data, you convert it to PC space. And this is the diagnostics you would get. Basically, CrIS would be converted to PCs, then the PCs go back to reconstructing the radiances just as a check that everything worked well, and these are just diagnostics, okay? And we also have a pipeline for AWS, which we just developed just a few weeks ago. Here we're interpolating, I'll talk more about that, how we interpolate AWS. AWS is very interesting. It has 4 feed horns, and each feed horn basically is a set of channels, and they're not looking at the same place at the same time. So what I do is I interpolate or remap the data so it only looks at group 2, the 89 gigahertz field of view. And then we do the same thing with the ERA5. Simple code again. So I showed you simple code before. Here on the left, I'm just loading up the files that has the weights. I call them the magic beans, like Jack of the Beanstalk. So it's the weights, very small files, and then you just apply them. These are 2 simple functions done. You can do the 1 day of processing within like 20 seconds, something like that. It's very fast. So here are the retrieval performance. So what I have is these are the retrievals from CrIS only on the left, and they're broken down based on cloud fraction. I know it's probably it's not too hard to read if you're in the front row. So basically it shows the different colors of different cloud fraction, and it gives you the sample size and all that. So, and then we have IASI on the right side. So let's look at IASI, for example. What is amazing about this result is that, again, it's machine learning all sky. You never want to do machine learning for clear only, for tropics only. You wanted to make it as diverse as possible with all the extremes. So the curve all the way to the right, the bad one, the one that has a large error, this is RMSE of over 3 degrees. That's for pixels, and that's about, I don't know, about 40% of all data, I think, is where it's 100% cloudy. So you can't see under the clouds, and there's a large error. The moment I can peek through the cloud a little bit, and that's at 99%, 99.99%, and I have to find out this significant digits. This is AVHR on the right, cloud mask or cloud fraction. So it might just be 99%. Immediately, it's not the purple, it's the red that is at 2 degrees. So it's remarkable. You just need a little bit of clear, just even 1% clear, and the algorithm will sort it out. And the same thing with CrIS too. The purple curve is all sky basically. So I got to figure out why IASI has a larger degradation when it's 100% cloud. versus CrIS, but I'm going to meet with Dorothy Copen later this afternoon to sort that out. But anyway, it looks pretty robust. And this is for water vapor 2, same thing, pretty robust. Now, a good test for sensitivity, how sensitive are we really to the cloud, is of course sea surface temperature, skin temperature over ocean. And I'm looking for cases where there's no precipitation at all, it's practically clear, or the total cloud rainwater is less than 0.01 millimeter. And you can see on the left column, 0 to 20% cloud cover is 0.67. That's a pretty good number. 20 to 40% is 0.65. That's also a good number. And then suddenly it jumps. So one had to say that, okay, where's the threshold where I'm really not affected by clouds? It could be 40%, but we have to do more studies and see how that ramps up. But you can see how that error on the top row ramps up nicely when it comes to cloud amount. And these are just images of the total cloud rainwater, which is a proxy for precipitation. So why we need these proxies is because once we provide you with the retrievals, you're going to get retrievals for every single pixels. They're not going to be QCs, like the calibration is a little bit off. Well, we can actually provide that information too. But what you need to have are environmental indicators. Is this clear or not clear? And so we want to provide that additional information. So request for one thing what we notice, and Liam knows about this, is that when you look at DB and you look at a section of ATMS and a section of CrIS, CrIS is a lot shorter because it needs more scan lines to do the calibration. They already have a fix for that, so I'm making requests if you could put that in direct broadcast. So that's one request. Another request is that I really need to know the VIIRS cloud fraction at the CrIS resolution. In order, I call them, instead of QC, ECs, but we can come up with another name, really environmental indicators, because I have to know where we have 100% clouds or 99% clouds. So I really need that. That's really important for this to work well. Okay, so now we're going to look at a interesting case study, because we're focusing on applications. I mean, in my old days, I would have stopped here. I'm happy, write a paper, everything's good. But at the end of the day, it's the last mile. The last mile is to use this information for something useful, right? And so we're looking at, we're going to be looking, let me go backwards a little bit. Am I going backwards? Yeah, no, I'm not. Hold it. No, going the wrong way. I'm still going the wrong way. Wait a minute. No, that's the end. How do I go front? Can you adjust it to start with, it could be any slide, just click on that. Yeah, I have to be careful with this clicker. Okay. So we're going to focus on this particular day. It's an interesting day and it's an extreme weather event, a lot of tornadoes, things like that. So I wanted to show you the, things about the retrieval. How does ATMS compare with CrIS by itself, with CrIS and ATMS? So I'll show some vertical cross sections, things like that. This is the statistics of that particular day global. If I only had ATMS on the left, not so bad. If I only had CrIS on the right, in the middle, better for some cases, right? But when you have clouds, it's a little bit worse, but in the upper levels, mid-troposphere, it's better than ATMS. But when you use both CrIS and ATMS together, that's the best combination out. So having a CrIS/ATMS algorithm is important. This is now, before I zoom into central US, this is what the retrieval statistics look like with ERA5. So these are differences on the right for 750 millibars, CrIS and ATMS together, ATMS only. The things that you don't see, things in a normal physical algorithm, you would see outliers due to precipitation. Remember, around the equator, you have the ITCZ and you have all these precipitation cells. You don't even see, you don't really see any indication of that because the machine learning just figures it out. And so that's impressive. The upper right is, differences when you use against ERA5, when I use CrIS and ATMS together, and then ATMS only. So you can see the difference is a lot smaller when you use CrIS and ATMS. So ultimately, you want to, if you have CrIS and ATMS, you want to use them together. All right. This is just the VIIRS cloud fraction for that day. And let me skip over this. How well does this compare to the NESIS operation algorithm? So we use radiosondes for collocations. This is for the entire 2025 of our machine learning algorithm against MIRS. So you can see 43,000 cases and much better. We do the same thing with MIRS and new caps. This is just for a day, so we have to do more of that. But you can see in the water vapor that that the machine learning does much better than MIRS or new caps for water vapor. Even new caps water vapor is worse than MIRS water vapor, which doesn't really make sense. And if you look at the retrievals, the purple is the IR, CrIS and ATMS machine learning algorithm compared to the green, that is the new caps. And they're very similar around mid-troposphere, but near the lowest layers, very different. I think we're maybe better by a degree or three-quarters of a degree RMS. So it performs well. Now, when I compare with the Aussie, which I only had a handful of observations, it's very comparable what we're doing with what EUMETSAT is doing, because EUMETSAT is using a machine learning algorithm too. So basically, physics-based algorithms are hard. You make different assumptions. Machine learning algorithms simply outperforms physics-based algorithms, especially if you have good truth. And ERA5 reanalysis is pretty good truth for training. And that's what people train, these AI weather forecasts that you hear about, NVIDIA, Google, they're all trained using ERA5. So we're being consistent with the training data set. All right. So now let's go back to this extreme situation, and we're going to look at cross sections. So this is just a cross section of, 37 degrees north from 100 to 80 west. And all I'm showing is the shape of the profile. So on the lower left, you can see the ERA5. You see this nice capping inversion. You pick up that shape when you use CrIS and ATMS together. And that's water vapor on the right. Let me just quickly go here. So this is ATMS. So look at the lower left middle, and you can see that ATMS does not pick up that structure. I think the problem is when I go backwards. I think can you go backwards? Yeah, one more. One more. Now just go back. Yeah, back and forth. Yeah. So you can see no structure in ATMS, go up one, structure in ATMS. Okay, structure and CrIS and ATMS together. Now this one is, if I use CrIS, all CrIS, 100, no, CrIS and just CrIS by itself. All sky, no matter what. And you can see in the middle lower, there's actually cloud contamination there. And you can see this big difference in the upper right, the top row, third over, you can see this difference. Now, if I say, wait a minute, I know I can go up to 99%. So what happens then? So this is 99%. So the things that are white now are thrown out and everything looks good. There's really no cloud contamination. And then let's say we're looking at maps of lifted indexes, and this is CrIS only by itself. Upper left is ERA5 lifted index. The middle is the retrieval. The right is the bias. And you can see cloud contamination clearly from CrIS. But if I say CrIS, I'm only going to use it up to 99.1 to make sure I include 99. A lot is missing, but you don't see any big errors. Everything looks good. There's contours there, which you can't see, but contours based on lifted index that says if it's higher, it's lower than this value because it's negative, that you'll have instability. So you see that looks pretty good. This compares 99% with 80%. You don't see on the errors on the right, you don't really see any issues. You don't really see something jumping out between 80 or 99%. So it works well, surprisingly well, up to 99%. And then if I do the same thing with ATMS, only show ATMS where the cloud fraction was 99%. You can see certain areas where the lifted index performs better using CrIS and ATMS because of that vertical resolution. Like you can see this big difference in the lower right from ATMS, which you don't really see in CrIS. And this is, if you only had ATMS, this is what the lifted index would look like, much better than just using CrIS everywhere. So ATMS by itself might still be useful for situational awareness. So I'm not throwing ATMS out, I'm just saying that CrIS and ATMS is better. All right, so we also have as part of the package, so the part of the package will include, can you go up one? Will include, yeah, just one. Yeah, perfect. We'll include these maps, but also for every single profile, we want to be able to automatically produce these SKU-T diagrams. So this will be additional information for forecasters. This is from CrIS and CrIS by itself, and this is ATMS by itself, which you can see the cape is a little bit different, not as intense as when you use CrIS by itself. All right, let's jump to AWS. So we're comparing AWS with ATMS. I did a comparison about a year ago, right? And the results were not so good for AWS, but at the time, I basically said, I'm doing retrievals at the single field of view retrieval. So when we did this comparison, everything was apples to apples, which I'll show you later. And the ATM, well, I guess the next slide will show that, well, almost. So I did a noise comparison when doing the retrievals. Can you go up one? Sorry. So when you do a retrieval analysis, you can sort of assume or make an estimate what the results are going to look like. So if you look at the lower, you know, the weighting functions or the 50 gigahertz channels at the lower from 25 kilometers down are basically the same. They're identical. You don't have channels in the upper atmosphere, so you know AWS won't perform well there. The water vapor channel is about the same, so it should be comparable. So you sort of have this feeling. The big factor is going to be noise, instrumental noise. So next slide, thanks. So what I do is I compute my own noise in a different way just to be consistent. And I use adjacent FOVs under clear skies in the tropics over ocean, under clear skies. And I take these differences, sum them up, square them, whatever, take the differences, sum them up, divide by square root of 2, and I get these estimates. And if you look at the right, these are ATMS values. For the channels near the surface, you're always going to get noise from the surface features. But once you get away from, when you get to the mid-troposphere, like channel 5, channel 6, channel 7, channel 8, like 0.2 degrees, that's very consistent from the official numbers that STAR will provide. When you look at the left, you can see the noise is a bit higher, but there's that one channel, channel 8, has a 2-degree noise, and then you can see some of the water vapor channels are pretty high too. So when I originally did this work a year ago, where I compared AWS with Tomorrow.io, with ATMS and Sumi, you know, from Sumi and NOAA 20, these were the results. So clearly ATMS was so much better than Tomorrow.io, as also AWS. Again, everything was single field of views, FOVs, right? It turns out, even with AWS, the FOVs overlap. With AWS, they really overlap. You know, there's 145 FOVs in a scan line, and they overlap crazy. And they're also looking at the different places at the different, you know, as you can see in the upper right, those are the scan patterns, and they're not aligned at all right? So I was recalling a few weeks ago, I said, hey, you know, I use this Backus-Gilbert technique to map ATMS to the CrIS FOVs. Let me do the same thing, the same process, but to, I'm going to pick AWS 2.1, which is only one channel, the 89 gigahertz channel. And so I did this Backus-Gilbert, which I'll show you another graphic. I'll go over that fast. At the edges, there's just not enough FOVs to average. So you can't include, when you do this remapping, you cannot, it's impossible to have 145. So you turn out getting 134, which is not so bad. Okay, I can do it. So this is sort of the mapping, how it maps. Like for ATM, I mean for AWS, we take all the pixels from the 50 gigahertz, which are 40-kilometer footprints, and just average them together at the location of the 89 gigahertz channels, and these are sort of the weights. So when you're far away, you just give it a small weight. When you're closer, you give it a bigger weight. So what are the results? The results are basically fantastic. So on the right was the original result. This is the new result. But let's compare it closer, because I did not, now I'm going to compare with ATMS with its own averaging to CrIS to sort of compare apples with apples. And you can see if you just look at the center and the right, which is AWS, they're virtually identical. So we got AWS to look like ATMS. And that's the important thing that I want to show here. So on the left here are difference maps, 500 millibars, AWS on the left, lower left, lower right is ATMS, and it's basically the same thing, very consistent. That's what the users want. They want consistency in the products. They don't want to say, oh, one is better than the other. You want consistency. And it's amazing that we got consistency. This is water vapor, same thing. Let me jump to this one. ATMS at CrIS FOVs, AWS, all interpolated to that 20-kilometer, pixel, and they're virtually identical. Maybe AWS is a little bit higher, but who knows? It could be sampling and stuff like that. And also the training was different too, because I didn't have 2019 for AWS. But they're basically very consistent. If I look at the errors, on the upper is the, let's see if I go one more. Okay, that's the retrieval from AWS for 850 millibars. On the right is the ATMS retrieval, 850. And you can't tell the difference. And the difference patterns are basically the same. So it looks really good. I'm happy. This is just precipitation products. And I'm going to conclude here. Just 2 more slides. So we have students developing what I call CSPP visualization. So when you get a swath, for example, you can plot all the profiles within that section, temperature, water vapor. Here's a nice cross section of water vapor up to, I can't even say, I think 700 millibars. And it really which shows the terrain over the Rockies, which is really neat. And you can almost see like a rain shadow or mixing water vapor shadow on the last part of it. And this is just another snapshot. Okay, so in summary, we developed these MLP weights for CrIS only, CrIS ATMS, ATMS, and EASI. We're pretty good. I'm confident there's nothing else for me to do with CrIS only, CrIS ATMS, and ATMS. EASI, I have to check some things out. AWS, it was developed for a few days of data, and I'll have to regenerate the weights for that. Retrieval performance, they're good. Outperforms new caps and mirrors. That's great. We plan to include these tools, application tools. We're working closely with partners in GINA we're hoping that maybe we'll have discussion time, but having like a northern latitude sort of proving ground with our friends from Europe and over the U.S. for the northern latitudes. And one thing, I'm working with UMetSat on comparisons with the Aussie. And finally, we think satellites, but there's part of the world that you have a lot of in situ observations. So I still think that it's very challenging to get to the lowest layer of the atmosphere, even with infrared. And so there's mesonet networks in the US that has temporal resolution of every 5 minutes that provides the key parameters for machine learning. And that's really the 2-meter temperature and dew point. And so we're going to experiment having a localized machine learning algorithm that combines satellite data with sort of in situ ground-based observation. Thank you.
Thank you, Mitch. I think we have time for a quick question.
I think your last point there on integrating surface-based observations in these retrievals is really important, because forecasters today using the operational NewCaps, for instance, often are told, make sure to adjust the sounding to the local surface temperature and dew point before you actually look at CAPE or whatever the other retrievals are. Just one suggestion, potentially you could use like a gridded like RTMA product over the United States, and then you don't have to deal with, oh, I need to figure out how to get all of these different mesonet observations. You already have a nice clean data set every 15 minutes that you could match up with the satellite data.
Oh, thanks. That's a good suggestion, and I'm glad I'm sitting next to you, so I could ask you more. And hopefully later we'll have maybe volunteers for people that will give us feedback. Because the most important part of this is getting feedback from users to see if these type of products are helpful to decision-making, forecasters, things like that. So